Assalamualaikum Ibu Retno.
Mas Sulaiman, how are you?
Fine.
Alhamdulillah, baik. How are you? Fine?
Fine, very good. Okay.
Thank you very much for coming webinar today.
Okay. Thank you, Ibu Retno. So we wait for others. Okay, this first time we have a webinar.
First time webinar with me.
So we need to learn how to handle this thing, this future trend, everything online.
Maybe the next time you and me and Faculty of Vocational Studies we can webinar too. Maybe one or two topic. Maybe for the writing of article like this.
For publication, maybe we can arrange.
Okay. Yes. In November maybe. In November.
Okay, no problem, Ibu Retno. Anytime, okay. Now we are free. We cannot travel now.
Okay. And so Pfizer, where are you from, Pfizer? From UITM or from Indonesia, Pfizer? Dr. Achilles Patak from India, maybe? Because the some people turn off the video, I think, but Mr. Harry, how are you? Oh, hello. Hello, how are you?
I'm good.
Are you from UM or from UITM? Dr. Sabiran Abu Bakar, are you from UITM or from UM?
Still student from Monash University. Student PhD student Monash University, Malaysia.
Monash, Malaysia. From Malaysia, Sabira.
Yes, from Malaysia, right. That actually from Aceh.
Okay, it's good. Okay, Pak Harry, you
welcome to webinar.
Yes. Yeah, Prof. Sulaiman.
Working from home. Good.
Yeah. So let me say to Brother Sabiran Abu Bakar, are you originally from Malaysia?
No, I am from Indonesia, Aceh.
From Aceh.
For right now, study at Monash University.
Monash University in Kuala Lumpur.
Yes.
Okay.
But your dialect like the Malaysia, not the Indonesia.
not quite similar. The most similar one is, I think, from Palembang, right? The Palembang people can speak Malaysia very well, very close. Which part in Aceh are you coming from, Brother Sabiran?
PD.
Oh, PD. So that's not quite hit by the tsunami, right?
Alhamdulillah, no.
All right.
I think there are from Prof. Agus Rubianto. Welcome, Prof.
Oh, this is my former supervisor. Where is he?
My teachers. Prof.
Yeah,
Agus
where is he?
Rubianto.
Professor Agus Rubianto. Professor Agus Rubianto. Could you please unmute your mic so we can talk?
Oh, welcome. Thank you very much, Prof.
Oh.
It's too long, yeah. We don't meet maybe 10 years ago.
Oh, yeah, it's been more than 10 years ago. Yeah. But the one that I can still remember that I asked your recommendations to apply for the scholarship, then I can go abroad. Thank you very much anyway. So far, I can come to ITS yet because the COVID. But I visited Brother Agus Muhammad Hatta. That's my college in Teknik Fisika, right? Yeah.
Yes, correct. Because as you went to Australia, I was in Berlin, yeah?
Yeah, that's right. That's right. It's been ages ago, but hopefully everything is fine and we are still at a good conditions, healthy, and that's the most important things.
That's right. This is very important. And also, how Professor Sulaiman? How are you?
Okay, nice to meet you again, Prof. Ruby, Pak Ruby.
Yeah. What Sulaiman? We are meet in, I think it's more, yeah?
Many places. in Bandung, in ITS,
Yes,
many times.
anytime. But as I was in Kuala Lumpur, I am only meet with the dean from
From UM.
Faculty of Science.
I see.
I then
Last
because
time.
we have the dean meeting, the dean sign off meeting in Kuala Lumpur last,
I
I
see.
think in 2019. 2019.
2019.
Yes, yes, yes.
Together with also Dean from Ailanga, Pak
Yes,
Wei.
yes, correct. And
Uh,
also from ITB. But now I am is retired from dean, yet is like is back again.
Ke scientific area.
So who is the dean at the moment, Prof. Agus Rubianto? Who is the dean for the science?
Professor Hamzah Fansuri from chemistry.
Oh, from chemistry. Yeah,
chemistry.
Hamzah Fansuri.
Yeah.
Okay, so another turn for chemistry, not always for physics.
That's right.
Okay, this is Dr. Akilas Patak. How are
Yeah,
you?
yeah, good afternoon, everyone. I'm good.
Yeah, good afternoon.
Actually, I'm from India, but basically I have just joined as a postdoctoral fellow in Chulalongkorn University, Thailand.
Oh, that's in Thailand, right?
Yeah.
How's everything there?
It's
Kapun cup. Can you say a kapun cup, the body cup, like that?
no, actually, right now I was just left from quarantine. I was in quarantine for 14 days.
Okay, yeah.
So
But
just
at
2
least...
days ago, I was just released.
So are you still in? So you're coming back to India at the moment, right?
No, I just on 23rd of September, I just coming back from India to the
Okay, good. So how long was your contract in Sri Lanka?
Yeah, it's for 1 year. So on 1st of October, my contract will be started.
I see. You're just about to start.
Yeah.
Yeah. So how's the COVID-19 outbreak there? Is the access for the laboratories already opened, or?
Yeah, almost they have opened because there are no any local cases in Thailand.
Oh, really? Few local cases. Okay.
Yeah. So there are only those cases are means they are increasing. Those are in quarantine.
So the quarantine is very successful there.
Yeah.
Oh, that's good.
So there are nearly, I think, 3,500 around cases are here.
That's just a few, man.
Yeah.
That's not that much.
No.
If you come to Indonesia, it's very, very hazard. This is more than 100 millions. Oh, sorry, 100,000. Yeah.
Yeah. I'm also from India. I just on 23rd of September, I traveled from India. So nearly 57 lakhs cases were there.
Okay. Yeah. Yep.
It's more worst.
Yes, exactly. So let's wait for Professor Paul Mukul, right? We need to wait Dr. Paul Mukul. Is he already here, or I could not see him yet?
I think not yet.
Oh, he's not here yet.
Not here. Mr. Mukul, I think the two.
Yeah, still another 5 minutes here.
There are 5 minutes again.
So 55 participants to start. Dr. Akhilesh?
Yes, sir.
How did you get this webinar so you know and can to join from your Chulalongkorn
Actually, one of
University?
my colleagues just shared me the link.
colleague in Kuala Lumpur or India?
No, she's in, I think, Algeria.
In Algeria.
Yeah.
Oh, good.
Yeah, just share me the link.
Okay, yeah. Yeah, might be Professor Dr. Paul Mukul from India, from Calcutta, share to other colleges, and then this
Yeah,
comes to
and
the Algeria, and then yeah.
yes, sir.
Okay.
One of the professor in CGCRI, that Mukul sir, is also,
Okay.
I just get some input from their researchers.
Yeah, yeah, yeah. Okay, this makes sense.
Yeah.
So your PhD, your doctorate is coming from India or other
Yes,
countries?
sir. Yes, sir. It's from IIT Dhanbad.
Oh, but yeah. So are you going? Are you working on the sometimes of bulk of optical fiber or?
Yes, sir. Actually, my whole research work is just focused on the fiber optic sensing.
Sensing with the Brillouin sensor or with the Brillouin or with other principle?
No, actually, I have performed both the experimental and theoretical works related with the fiber sensors. So
Yeah.
on that, for the theoretical works, I have used console multiphysics softwares. And right now in the postdoctoral fellowship, I am just learning for the MATLAB. So right now I'm working on the MATLAB too.
So this kind of a bit more simulation and modeling, yeah?
Yeah.
Okay. Have you been working with some guys in like of the City University of London?
Yes,
Kind of
sir.
yeah, because they are very, very good and strong in simulations and modelings for the fiber.
I was there in City University of London under Professor.
Oh, really?
Yes, sir.
Good, good. Then
I was there.
could you please tell me how is going on there?
Actually, sir, in 2017, I was in London under Professor B.M.A. Rahman. So I closely worked
with Professor Rahman, right?
Yes, sir.
B.M.A. Rahman. Okay, yeah. Then.
And then at that time, I was just exchange program for 6 months. But during that 6 months, I have learned a lot from him.
Okay.
So my whole theoretical works was his only.
So have you been the Gratan, Professor Gratan, Ken Gratan as
yes,
well?
Sir. Professor Gratan and Dr. Arti Agarwal and Professor Tongshun.
Tongshun, yeah. Okay, good. I just contacted by email and discussing on Zoom to initiate the collaboration between the University in Indonesia. Then, but the COVID struck at the moment. Then everything can be cancelled. So yeah. Hang on. Oh no, I thought that someone is coming. Oh, that's great. So you're pretty much ready for the discussions after the talk.
Yeah, sure, sir.
Yeah, the purpose we are doing this webinar is actually to get the international exposure for all of the Indonesian academia and researcher, initiate the collaborations and share all of the facilities and the experience. So that's just the aims why we need to do some, let's say, scientific communication, right?
Yes, sir.
Okay. Nurul Hidayah. So working, yeah, Prophet, no?
Are you sure that Dr. Walid and Dr. Mukid?
Dr. Walid will be available at 3 o'clock. So we're just waiting for the attendance of Dr. Mukul. So I will contact him on the other screen here. Give me a second.
Muhammad Zulkarnain. Mr. Edo? Mr. Edo?
Yes.
Yes.
Okay.
Have you sent the link of Zoom for the two speaker and the Prof. Sulaiman?
Yes, I have sent both of them, and I have checked again. So please wait a minute. I will contact him again.
Okay, thank you.
Prophet, no?
Yes.
This Miss Riri says that there's a lecture at this moment. So maybe the opening could be done by someone else because Bu Riri is on the lecture now. He sent the
Prof.
on the
Sulaiman,
WhatsApp messages for the opening. Who is going to be
opening.
on the opening speech?
After this, who is the speaker? Prof.
The
Sulaiman?
speaker is going to be Dr. Mukul first because Dr. Mukul just available for an hour, and then Dr. Walid and Prof. Sulaiman come to last.
But both of the speaker not ready now.
Yeah, it is going to be ready. So I'm talking about the opening speech. Who is going to do this one? Uriris or someone else? Or Mr. Yasin?
Yes, dia anu tuh. Maybe he is busy. I'll call this just a moment, please.
Dr. Mukul has a problem with the connection, I think. He's already got the link. Maybe he's already got the link, but he can't join due to the password. The password is invalid. Or might be because the spelling, because the committee just provide the spelling as a photonic without S. So I will remind him. Should be with S, photonic, right? Not coming up? Not turning up yet? No. Yep. Hello.
Hello.
Dr. Mukul.
Yes.
Yeah. That's so sorry because the spelling is not correct. That's photonic without S.
Okay.
Yeah. So you're in the room now. So please,
Yes.
could you please turn your camera on? So say greeting to all of the participants. We are not started yet. Okay, good.
Okay.
All right. So just say to someone else that you know, and there's a Dr. Achilles from India.
Okay.
You might recognize him. Yeah, he's got this link from his college in Algeria.
Okay.
Just say something.
Okay.
Okay, Dr. Moko, you are in your lab, MCVD
Yes.
behind you.
Within this lab. This is
Okay,
Oh
very
yeah,
good.
the connection is not very good. Yeah. So your camera is stuck, Dr. Moko.
Dr. Harry,
Yeah.
Mr. Diazes cannot join because there are meeting.
Okay.
Please, maybe you can start today.
Okay. Yeah, that's fine. All right. Hang on. We need to wait the connection from Dr. Moko Paul. Oh, she left. He left. Huh? Yep, you are in, Dr. Mukul, with different account, I think, because your name is a bit different now. Shailendrakum something. But that's fine. Can you hear me, Dr. Mukul? Test. Test. We have someone from bppt, Bu Ratna, Yanto bppt. So they're from research body. We have Ms. Kartika here from student in biomedical engineering, Master of Biomedical Engineering.
Oh, Kartika. Okay.
Yeah.
Yeah, okay.
And some of them are, I think from
as Chang, from where are you? Where are him from? Chang.
which one? Which one? Oh, XS Chang. Okay.
Okay.
Hello.
Chang, I don't know whether the spelling. Chang. Hello, Mr. Chang. Oh, welcome, Dr. Agus. How are you?
Halo, Assalamualaikum.
Waalaikumsalam. Oh, this is
Prof. Sulaiman.
brother
Your brother,
Agus.
Mr. Harry. Your
Yeah,
brother,
yeah.
Mr. Harry.
Hello.
Assalamualaikum.
Assalamualaikum.
Waalaikumsalam.
Actually, there is some problem in the internet.
Yeah, that's fine. I saw your name is a bit different, so maybe it's coming from a different Zoom
Yes,
account. But that's completely fine, as long as the image, the signal is fine. So you come back to this room, right?
Ini video kita dah off kan?
All right. So it's already 2:10, so we have a start.
Okay, okay.
Could anyone or the committee switch the mic off for a moment, because we're gonna have a start, the opening speech, and as well as the lecturing from Dr. Moko. So first of all, representing of the Dean of the Faculty of Science and Technology, we call it Science and Technology instead of Science and Engineering. I have no idea what's different is, but at least we have two departments or two different things in our faculty. Sciences, which is math, chemistry, biology, and physics. as well as the engineering or technology. We have the informatic systems, environments, as well as the biomedical engineering. So along this faculty, we had couples of research groups, and one of the research groups is coming from our Photonics laboratory, which is about the optics and its applications, lasers, and the communication systems. So this webinar is one of the World University programs, world-class university program from Airlangga University to initiate the collaborations, communication, and things we can share from what you experienced and what we had, as well as our facilities and what you have abroad. So hopefully by doing this webinar and scientific communications, we'll get more engagement between ours and yours laboratory and expertise. So thank you very much for the comings and participate, for all of the participants and the delegates. Hopefully you enjoy and have fun, enjoy the webinars, and we are ready for the first talk coming from Dr. Mukul. So Dr. Mukul is actually coming from India. Let me open his CV here. I'm working on two screens, so if it's still left and right here, so sorry. Because on this one screen zooms, it's hard to handle, so I need to have to screen here. Yep, give me a second, please. Oh, basically, there's a lot curriculum vitae. It's very, very strong and high focus in ceramics and optical fibers. So any one of you who is interested into the ceramics and the optical fibers in any materials, here is the expertise, the one of the most crucial researchers in India, with all of the collaborators, most of them coming from, is there any, the Russia one? And yeah, so this is in the Jaipur University in Kolkata. So please, let's see, the virtual stage and microphones is yours, Dr. Mukul. So time is yours. You can have a start. Thank you.
Okay. So good afternoon to everybody. It is my great pleasure to accept my invitation to deliver this talk. Basically, I will deliver regarding our specialty optical fiber for photonics application. Basically, our lab is dedicated for making of specialty fiber for different purpose. Now this is my talk for photonic application. Next slide. Now I will see what is the specialty optical fiber. Basically, specialty optical fiber have some special property which is distinguished from standard fiber. If we see from viewpoint of application, this except our communication purpose, we have some application in a basically laser surgery, high power laser, automatic and aerospace. So viewpoint of material part, it may be silica with some incorporation of fluorine or chalcogenide, maybe polymer, maybe incorporation of other codopen, and also some metal. From viewpoint of processing, it may be cladding, coating, and post-drawing treatment. And design is maybe solid core, hollow core, or multi-material. Now is a huge demand in now at present regarding the basically for specialty optical fiber. It is in front of this in a global market. If we reach around 15,000 by 2024 and 2019, it is reached 1,171.9. And by viewpoint of application wise, if we see, they have global market survey So that actually for telecommunication it is around 1,582 million US dollar in the market. In a healthcare, in a 507. So total is 533 million US dollar market. It will be reached in 2022. And this is just some slide I am giving, taken from some paper published. This is the basically multi-material, multi-structure, silica, polymer, chalcogenate, telluride, and all kind of this region. And this is the polymer optical fiber region. And this is the conventional single mode fiber. This is tape-inlet and silica material. Now, if we see the periodic table, almost all the elements have been used for making of the glass, and not only in the glass, in the optical fiber, all kind of material. So there is, but if we take a combination of different material, there is a huge opportunity in the research for making of development of another special kind of fiber. Now in the 2009, it was celebrated 150th anniversary of the periodic table of the element, where it was highlighted that this periodic table has a tremendous role in chemistry, physics, biology, astronomy, engineering, as well as signing a breakthrough specifically in the field of glass and optical fiber.
Sorry, Mr. Walker, can you view full screen? Because
Full
it's
screen.
better. Yes, the
Okay.
full screen is
Okay.
better. Thank you.
This one. Slideshow. This is slideshow.
Yeah, you can do slideshow anyway.
Correct, slideshow.
Okay.
Yeah.
Now
It's
clear?
better. Thank you.
Okay,
Yeah, thank
okay.
you.
Actually, in a facility of fiber activity in CGCRI, different fiber, MCBD solution doping technique, basically RBM, terbium, stack and dop process for photonic crystal fiber, hollow core PCF, MCBD solution doping metal nanoparticle and multi-core optical fiber, and also nano engineering optical material fiber, and also RBM dop intrinsically photosensitive fiber for distributed feedback fiber laser and photosensitive fiber, and also some chilled delivery, which has been used directly for making of high content of ytterbium and thulium doped fiber. This is a different structure we have fabricated for microscopic view of the different kind of facility optical fiber. Now, main thing of the objective is that here we will present some facility fiber with incorporation of rare earth along with some ceramic oxide. This is basically aluminum, scandium, zirconium, yttrium oxide, along with some material study, TEM, IREX, SPX, XRD, followed by some different process fabrication parameter, and lastly we will come study of spectroscopic property and amplification, lasing also. Now, ceramic, this is used aluminum oxide, zirconium oxide, yttrium and scandium. This is nano engineering glass. Basically, these form nano sizes phase separated particle which is incorporated with rare earth within the glass. This is basically used for a broadband optical amplification and moot lock fiber laser. Why selected aluminum, zirconium, scandium, yttrium in a ceramic oxide along with rare earth? First thing is reduce the clustering phenomena. It increased the solubility of rare earth, increased the reflectiveness of the glass without any adverse effect, and increase on the non-linearity of the fiber, making of a large number of non-bridging oxygen, and it also make defect generate from phase separated nanoparticle which will favor the spectroscopic property of the fiber. First come to RBM, the special kind of fiber which we have developed for broadband optical amplification. This is the process. This is basically phospho, yttrium, alumina, silica gas glass. This is MCBD solution doping process. We deposit phosphosilica layer, then incorporated RBM, aluminum, scandium, yttrium into the glass phase, then make the dehydration, oxidation, sintering phenomena, collapsing, and then finally, after making of the preform, we do close in the furnace annealing of the preform done 1200 degrees centigrade at a cooling and heating rate of 50 degrees centigrade per minute. This is the vital step for generation of nano-engineering particle within the core glass of the fiber, which will improve the spectroscopic property with respect to particular type of application. Then we dot the fiber from this annealed preform. Now this is the step. We deposit MCBD, deposit porous layer. After deposition porous layer, we soak with different kind of element from the solution phase. Then this is the sintering. After deposit soak layer, this burner move, and then oxidation, dehydration, sintering take place, and finally collapse and make a preform. This is the MCBD solution doping process. Now we come to the some characterization part. This is the microscopic view of the developed fiber in a scandium yttrium glass based matrix, where this is the standard fiber cross section, this one, and this is a scandium dope glass, and this is the electron diffraction pattern, and this is stem. Here you will see some nano phase separated particle in the glass, and this is the basically another glass. This is done after annealing, and make this annealing, it is gives rise to yellowish colors. That means scandium is incorporated along with RBM into phase separated particle, and this is the after annealing it form a particle, and if we beat the high resolution tape, and this crystalline structure will develop, and this is the iridescent spectra which is showing some diffraction plane of the glass matrix, and we have taken the iridescent spectra on the particle, and out of the particle it is showing that on the particle there is a huge content of aluminium, yttrium, erbium in a region, and out of the particle, this means this region there is a less yttrium, aluminium and yttrium. This is the microscopic view of the fiber. This is the earlier case preform. This is a high resolution tape along with the spectra we have taken, and this is showing this particle will develop along the core clad boundary, and we have measured this kind of fiber in a diameter of different 8.5, 9, 9.25 micron. And here we have not found any imperfection between the core and cladding layer, and color of the glass become brownish yellow. This brownish glass confirm that glass converted to the nanophase separated particle within the glass, and this we have developed this yttrium aluminum garnet along with this kind of compound in the form within the glass matrix, and iridescent spectrum so this particular was present in a crystalline state, not the amorphous. This is the count we have taken on the fiber, because in the fiber step it is very difficult to characterize all kinds of phenomena, and showing this region is a yttrium, aluminium and rich, and this is less yttrium, aluminium, and composition of this phase separated particle was evaluated from IREX analysis by focusing the ray particularly on the particle. And we have taken EPM analysis. This is electron probe microanalysis to detect the distribution of the each element along the diameter of the fiber. This is a scandium, aluminium, yttrium, erbium, phosphorus or region. And this is the reflective index profile we have measured the fiber. And also done XPS study. This XPS study show what kind of structure form within the glass, this kind of new class of matrix material. This is done basically preform sample. From this sample, we have shown that such kind of scandium and yttrium is separated in a nano environment surrounding the erbium ion in a nano engineering glass, and which is shifted with the binding energy. This shifting of the binding energy of erbium, aluminium and yttrium showing that the erbium is present in a different surrounding environment compared to the other matrix. This is a very, very tough job for analysis of this material in a fiber. Now we have measured the absorption phenomena. of the, it is see that absorption is starting this one. This is a basically scandium phi, this one, and this is the nano engineering. It is showing some broadening of the structure, and after annealing it was showing the some spectra peak arise. This peak suggests that RBM is present in a nanocrystalline structure, and this is the basically three fiber we have taken. This is the nano engineering, and this is the Swiss-stone fiber before heating, and this is the normal scandium phi. This is showing, this is the broadening of the fluorescence peak arise. This broadening arise due to the presence of RBM, this new kind of glass in a crystalline matrix. And we have also measured the basically pump power, emission power with variation of the pump power with respect to the particular type of length. This is the nano engineering developed new kind of fiber. This is the before annealing, not nano engineering. This is the standard fiber. It is showing under the same condition of the measurement of the emission power of this nano engineering class is signal intensity is very, very high compared to non-nano engineering or normal RBM doped fiber. So main conclusion is that we have developed RBM doped special kind of new glass-based ceramic oxide glass-based fiber which show strong emission, and also it show a huge large broadening is almost covered to the C+11 region because of the presence of RBM in a nanocrystalline force, and fluorescent intensity also is high. So this kind of nano engineering fiber will be useful for broadband optical communication system. And we have also measured the basically lifetime, fluorescent lifetime measurement of the RBMR. It is showing that this kind of nano engineering glass-based fiber, basically this is showing the fluorescent lifetime 11.3 millisecond compared to normal fiber 9.9 and non-nano engineering 10.16. So this kind of large lifetime of RBM indicate that RBM is present very, very low phonon energy particle which is composed of mainly scandium and yttrium oxide. This is the, we have measured the gain characteristic. This is the optical gain and noise figure. It is showing that nano engineering glass-based fiber, the broadening and flatness is too much high. It is almost beyond 16,000, 1,600 nanometer. And this is showing so that this is also some kind of fiber which I measure also noise figure. This noise figure also show this is a very, very low compared to the other fiber. This is nano engineering, and flatness of the gain flatness is 0.7 plus minus within 1530 to 1590 region. And this is the basically three fiber we have measured. Maximum gain RBM dope 39.45, RBM dope normal fiber 37.5, and 35.89 is RBM dope fiber. And flat gain region 1530, 1509, 1530, 1575, 1530, 65 region also. And flat gain 38.675, 36.76, 36.5. And gain variation 0.7, 0.67, 0.82. And noise figure 4.35 to 6.85, 4.61, 7.15, 5.570. So from viewpoint of optical gain, flatness and noise figure, this kind of normal special kind of RBM doped fiber is a huge advantage compared to other normal RBM doped fiber as a broadband optical communication system. Now I will describe another fiber. This is intrinsically photosensitive RBM doped fiber which is used for distributed feedback fiber laser. This distributed feedback fiber laser will be used for making of optical hydrophone in a submarine system for defense application. This is basically we dope more than 25% germanium dioxide, and no hydrogenation process will be required for writing of the gating, and incorporation high germanium create a high defect of germanium oxygen whole center, and high doping of erbium without any clustering make a making of the intrinsically photosensitive of the fiber. This is a core composition, germanium, silica, erbium. This is aluminum erbium oxide. Cladding corporation either silica, silica porine. Core diameter is 2. This is a very low core diameter. It is a high Na. This is high Na, low core diameter base, intrinsically photosensitive fiber, where germanium doping is around 20 to 25 mole %, and erbium is very low, 50 to 100 ppm. Background loss 10 dB. Absorption 3.5 to 5.0 dB, fiber diameter 125 micron, and resin is acrylic resin. Now we have make, this is a modified chemical vapor and this is solution doping. This is use silicon tetrachloride and erbium chelate compound. This is one kind of organometallic compound which can be vaporized at a around 300 degrees centigrade with flow of helium, where erbium oxide can be incorporated directly, and then germanium. But here is a erbium oxide is incorporated using erbium chloride solution along with aluminum to make a free form. This is a one process, directly vapor deposition, and this is a MCBD solution doping process. And this is done porous layer for making of the DFB fiber, and this is a setup for MCBD setup for making of the P-form. What we do? First, we make a P-form, then we make a rod, 2 millimeter. That rod is actually insert into a 10 by 2 millimeter size tube. Then we draw the fiber from this stack P-form, so that the core diameter comes down around 3 micron. Otherwise, this is stack and draw process. Otherwise, it is very difficult to reduce the core diameter. And we have made different fiber. This is a newfound fiber, and this is our developed fiber. This is a doping host is silica germanium, another doping host silica germanium aluminum oxide. And this is make some clustering effect to reduce the ledging efficiency. Because distributed feedback fiber laser, one of the part is intrinsically photosensitive erbium dope fiber, where no hydrogenation process will be required for making of the phase shifted fiber backgetting. This phase shifted fiber backgetting writing on the photosensitive fiber will be used for making of the DFB fiber laser. This is the main part. And this is the actually basically microscopic view. This is a very small core diameter. And this is the absorption loss. This is around 4 dB per meter. Absorption loss at 980 nanometer. And this is different kind of fiber. Another fiber we have used and also measured the loss. And this is the EPMA curve. This is a huge amount of germanium. If you see, this is 25% of the germanium. This high amount of incorporation of germanium along with erbium, this will create a intrinsically photosensitive fiber. Now this will make a backgetting. How to write a backgetting? This UV laser source will be used argon ion at 244. Then we make plies of the erbium dope fiber with this Corning HI10 Corning fiber, and then we optimize the length of the backgetting, phase shifting location and coupling coefficient. Then length of the gating also alter with scanning length of the UV during FBG fiber backgetting inscription. And then we also establish the DC phase jump equivalent to 5 phase shift in the FBG period by moving the phase marks using a piezo stage. And coupling coefficient of the FBG also alter by varying UV influence. Now gating spectrum was observed online during fabrication of the photosensitive fiber backgetting using optical spectrum analyzer. This is the actual curve. This is the ledging peak out spectra at two different pump parts, 64.6 milliwatt and 106 milliwatt. And this is the basically threshold pump, and this is the basically reflection spectrum of the gating, and this is the basically transmission spectrum of the gating. This DFB fiber laser we have developed along with the fiber we have making, and we have connected to the defense lab. They are making of the basically for hydrophone, fiber optic make hydrophone, which will be now using in a submarine system. Each submarine require almost 3,000 DFB fiber laser that are we are involved at this present state. So now come to the conclusion. We have developed new kind of erbium doped nano engineering glass-based fiber, which is basically scandium, phosphoyttium, aluminum silica, which will improve the optical amplification property, not only from viewpoint of intensity, as also the broadening of the wavelength, so that it can be used as a C+ L band. Another thing is that gain flatness is also less than 0.7 dB plus minus, and is also 38.675 dB, also gainless. And this kind of nano engineering glass-based optical fiber-based erbium doped amplifier will be used for basically broadband optical communication system. So come to this is acknowledgement. This is our fiber optics group, Photonics, Mexico, CIO. Some colleagues also involved on a collaborative work. Another is fiber optics group, University of Malaysia, basically for Suleiman group, and also some Waterloo University of Technology, Naval Research and Oceanography, and Department of Science and Technology, and Council of Scientific and Industrial Research. Thank you very much for your kind attention.
All right. Thank you for your sharing, Dr. Mukul. So
Yes.
now we come up to the question and answer sessions.
Okay.
So anyone who want to ask some questions, you can just unmute your microphone and speak up what you're gonna share or you're gonna ask. Okay. Anyone? So while we are waiting the questions, I just saw your XPS measurements on your first experiment, I thought.
Yes.
As long as the XPS needed for the characterizations or whatever in your samples or in your surface, is that you're supposed to have the profile of the depth concentrations of your materials on the surface, or you, because XPS is just a few of nanometers in depth,
Yes.
right? So so in your samples, what kind of the configuration you have erbium than what before you end up with the silicons on the substrate, right?
Yes, yes. Actually, what we do in a P-form. This is basically 10 millimeter diameter. Within the 10 millimeter diameter, maybe 1 millimeter in the central portion region, all the codopen are incorporated. Okay. This P-form actually cut down and polish both surface, and it make a cylindrical shape. Okay. That length may be maximum 1.5 millimeter. Okay. Thickness, that is called. And basically this profile actually on the surface means here actually we determine what is the actual environment of the erbium, surrounding environment of the erbium. Okay, that means where erbium is linked to yttrium along with aluminium. Okay, if it is erbium is alone, then binding energy will be low.
Yes, exactly.
If it is combined with a crystalline state with yttrium erbium, so that binding energy will be shifted to the higher region. So from this binding energy profile of the erbium certain 1p 2p band, it can give an idea how will be the surrounding environment of erbium present this nanostructural basically material. We basically here we are done on the surface region. Surface region means if it is surface, but in the inner side same profile, surrounding environment of the erbium will be still.
Okay, if you can share again your XPS result, the compositions of your XPS, how much the percentage of RBM in comparison to the yttrium and germanium or whatever you.
Yes,
From
yes.
my memory, there are three main components on the XPS results. If it's dominating, the RBM is a bit more prominent. So that's kind of the shift of your binding energy is going to lower binding energy, right? Instead of the higher binding energy, because you have more than one components
Yes,
instead
yes.
of only the erbiums. How many percentage did you got from the XPS analysis?
Actually, basically, if we make
Yeah.
quantitatively for how much element is present, this
Yeah.
can be most useful tool is EPMA, electron probe microanalysis.
Okay.
From XPS study is give a qualitative idea.
Yeah.
How much present. This is actually not actual measurement for XPS. XPS give an idea about the surrounding structure of the rare earth compared to the other portion. But
Okay. Yeah.
for
Yeah.
how much element actually present, that can be detect basically EPMA that I have seen in some slide. This can be measured along the diameter of the Dove region
Yeah.
distribution. Each element, not only RBM, but also other aluminium, germanium, yttrium, that can be give a perfect quantitative idea about the distribution of the each element.
Yeah. Yeah. I got what you meant. Okay. So let's come to the audience, the participant. Is there anyone who want to share or ask about some questions? Ready? Okay. Could you please raise your microphones and then speak up to the.
Can I
Okay.
ask
Yeah.
a
Good.
question?
Yes.
Okay, I have two questions.
Okay.
First question, why you call your fiber nano engineer?
Okay.
If you can explain the difference with the other fibers in terms of
Okay.
design. And the second question, why we need the small core fiber for DFB application? What the advantage of the small core, to have smaller core, around 3 micron?
Okay, okay. So in your first question is that regarding what is the advantage of nano engineering glass-based fiber compared to other. The nano engineering glass-based fiber means that there will be a RBM which will be present in a nano phase separated particle. That nano phase separated particle size will be maximum 10 nanometer, so that the radiation loss will be low. The each other element is present. These nano phase separated particle have a low phonon energy compared to the rest of the matrix. If it is present pure silica glass amorphous, the phonon energy will be high. Okay. If some maybe 70-80% RBM will be present in a nano phase separated low phonon energy glass, because low phonon energy, because the content of silica is low. That has been confirmed from radiation energy. This low phonon energy is present. It will improve the spectroscopic property of the any rare earth from viewpoint of amplification, from viewpoint of intensity, as well as also clustering phenomena. This is the first question. Regarding the second question in your question, regarding the DFB fiber laser, why people are used for a basically low core. That means low core, not only the low core, it will be also high NA. Because for first thing is that for any kind of writing of the gating, people are using normal fiber germanium and then go to hydrogenation process around 7 days at high pressure. But in this case, we have incorporated high Na, high germanium. This will be around 20 to 25%, because this high content of germanium will give large number of germanium oxygen defect center, which is sufficient for not required for hydrogenation process, for writing the gating. This is the first thing, that it should be intrinsically photosensitive, no require any hydrogenation process because of the high content of germanium. If we incorporate high germanium, that is 25%, that means this should be high Na, around 0.3. If we make the design, waveguide design, cutoff will be less than 980. So accordingly, core diameter will be low. That means around 3 micron. That is why for intensity photosensitive fiber, for writing fiber backgetting, this fiber will be high Na, low diameter base fiber.
Okay. Thank you, Dr. Moko.
Okay, thank you.
Okay, thank you.
Mr. Harry, maybe the share screen is closed. Maybe we can interact with the discussion. I think like
Okay,
this.
okay, thank you. Stop sharing.
Okay. Good afternoon, Dr. Harry. Can I ask a question?
Yep.
Yes,
sure,
yes.
for sure.
Welcome.
Okay. Thank you very much, Dr. Mukul, for your interesting and inspiring presentation. So very interesting that you nano-engineered the fibers for some interesting applications. So I believe that it's give a lot of opportunity for doing research and as well as to explore new applications. Yes. So I just have a simple question. Okay. I wonder how do you manage to fabricate such doping in your fiber system? So you have how do you get some materials? I mean the doping materials. Do you fabricate or do you produce by your lab, or do you get from the commercial products?
Yes, actually, our lab basically, in our lab, it is dedicated for making of facility fiber. All kind of fabrication facility is available for making of fiber. One of the process is the MCVD process, modified chemical vapor deposition process. This modified chemical vapor deposition process, we use different kind of source material for incorporation of different kind of codopant. For rare earth, erbium chloride, ytterbium chloride, and silicon tetrachloride, germanium tetrachloride, aluminum chloride. Okay, but for MCVD process, CVD process, this is incorporated in a vapor phase, which is available in a liquid state. Silicon, germanium, phosphorus, this is available in a liquid state, so it can be easily vaporized and can be incorporated. But for rare earth, erbium chloride, aluminum chloride, lithium, aluminum, this is a solid, so it cannot be incorporated directly by MCVD process. What we do, we first deposit in a porous layer, silicon germanium porous layer, and low temperature inside of the silica tube. Okay, then cut down that porous deposited silica tube. Then we make a solution, alcoholic solution or water solution of certain strength of aluminum chloride, rare earth chloride, and then after making of the solution, that porous tube in a deep into the solution for 1 hour. Okay, then it means all the codopant which is present, aluminum, erbium, this will be soaked into the porous layer. After 1 hour, solution is drained out and dying to remove the solvent. After removing the solvent, that aluminum chloride, erbium chloride which is present in a solution will be stay in a porous medium of the pore. Then will be fixed up into a chart, lead working chart, and then increase the temperature 1400, 1800 degrees centigrade, gradually increasing the temperature, that solute which is present will be converted to a oxide, aluminum, erbium oxide, and fused together will be a glass. And in this way, we make the preform, and using the, this is the fiber drawing tower. Using this fiber drawing tower, we draw the fiber. This is the step.
So that's actually very start from the scratch, I think, Dr. Hatta.
Okay.
So Dr. Mukul started from the scratch, from the materials, they create the solutions, then use the techniques as what is supposed to have the liquid, which is, there's a lot of works based from the start, rather than use the commercials components, but all of the characterization is actually already carried out, and then this is quite awesome that all of the criteria and the details of this are appropriate for the next applications. Okay, any other questions coming from the audience? Do you still have 2 minutes for this first?
Sorry for disturb.
Time. Ready. You can have a questions.
Yes.
Okay.
I heard about the research for the optical fiber with the ceramic oxide doping. I heard of the aluminum oxide, zinc. Wait a second. Gl2. Is it the yttrium or scandium? Why the I know that the rare earths used in the laser solid type. Sorry, my English is bad.
Yes, okay.
But
no problem.
The point is, rare earths is used for the solid type laser, including neodymium YAG laser, neodymium, yttrium, yttrium, aluminum garnet laser. Why? My question is, if we use the rare earths for the doping optical fiber, is it the result is the same as the oxide ceramic for the optical fiber doping?
Yes, I understand your question. Actually, you want to ask what will be the advantage of fiber laser compared to ceramic laser, bulk laser? Is it my correct?
Yeah, I think so. That's what Rary is supposed to have the answers.
Yes. Actually, everybody know, actually ceramic oxide, this is a bulk glass that is also in our another lab. We are doing glass lab. They are doing basically bulk glass based laser. This is basically neodymium dope phosphate glass, and also some yttrium oxide, ytterbium, ceramic. But main advantage, there are two advantages. One is the fiber laser is basically, this will be some advantage being from viewpoint of it will be high intensity, high power compared to the bulk laser. Another advantage is that beam quality of the fiber laser is very much perfect and good compared to the ceramic based any kind of bulk laser. This is the two advantage.
Okay, Rari, is that clear for you? So that's the significant difference between two glass, because Dr. Mukul is actually working on two different things, glass and ceramic fiber lasers. So this is a bit different, and Dr. Mukul has already performed what kind of the materials on both area. So that's the beneficial. We are using the ceramics, which is I think that's a lot of cheaper than the glass things. All right. Anything else from the audience that you need to ask to Dr. Mukul? We still have another just 1 minute before we move to the second speakers. Anyone else? Dr. Akhilesh, would you like to ask some questions in terms of the simulations or modelings?
No, sir. Thank you.
Okay, good. All right, I think that's all for the first sessions. We very thankful to Dr. Mukul Chandra Paul, and for all of these sessions, we just to emphasize that regarding to our discussions here and to our collaborations that we have already done a couple of years back, so hopefully we can get more engagement, not only from Indonesia's institution in Malaysia, but as well as from India and other countries. So thank you very much, Dr. Mukul. You can stay if you want, but at least the second part, the second session is coming from Dr. Walid. I want to say hi and hello to Dr. Walid.
Hello, how are you?
Assalamualaikum, Dr. Walid.
Waalaikumsalam.
Yeah, we are perfectly good, and hopefully everything is good in Thailand, in Bangkok.
Thanks.
So for Dr. Akhilesh, the second speaker here is as well as from the Egypt is actually, yeah. You're originally from Egypt, but you are affiliated with the Bangkok University in Thailand, right?
Yes.
So this is the hang on, I need to open the CV from Dr. So Dr. Walid. So you are at the moment, oh, you are not in your lab, Dr. Walid?
No, I'm at home today.
Okay, yeah, you have work from home. So Dr. Walid is actually finished the PhD graduate from Orlando, USA, right?
Central Florida. Yeah,
Yep.
Central Florida.
And as well as your master degrees there. And then, but you're originally from the computer engineering in a University of
Cairo University.
Cairo. Yep. Yeah, Cairo University. Yep. And your qualifications here is pretty much, oh, you're doing couples of Monte Carlo and simulation, right? And modeling.
Yeah, I did that. So now I'm doing it again, but yeah, we do.
Okay.
Do as Manitoba.
Okay. Okay. And this is your current work. You have the research scholars from Bangkok University. That's why you moved to Bangkok, right?
Yep.
Okay. And oh, that's a lot of experience in Toronto, Canada in 2004.
Yeah.
Okay, good. So as we would like to have the real stage now, the speaks and the microphone and stage is yours, Dr. Walid.
So I just share the screen, right?
Yeah, sure. You can share your screen.
Okay. I will start.
Yeah. Okay. So enjoy all the participants. Then you could have questions and discussions about what Dr. Walid's present. Thank you.
Okay. Are the slides clear? Okay. So
yes, this is clear.
Okay. So my topic a bit more about the recent work we have been doing both at Bangkok University. It was collaboration with AIT, or Asian Institute of Technology. So the work is effect of the polymer swelling on optical scattering, mostly for VOC, or volatile organic compound sensing application. So here we deal with two things, which is the scattering by surface roughnesses, as well as the effect when a VOC is present on the polymer, and how the swelling process can be used for sensing. So I divide my work in briefly introducing what have we done before in polymer optics. I mean, basically our group and collaboration, and some examples of the work, and what. Yeah, do you hear me now?
Okay.
Yeah. Okay. So and what's new, or what bring the interest back for us into the polymer optics, basically was the development of 3D printing that allow us to, or allow the technology to develop printing optical components with the 3D printer, where we made some waveguides, and we will see how that pushes toward the developing of sensors. So basically, polymer optics is not a new topic. It has been there for decades and decades. One basic example is a plastic optical fiber, which if Dr. Mogul before we talk about fibers, one of the cheap candidates are plastic optical fiber. They are typically used in telecom for the last mile or so. And the good thing about them, they're cheap. I mean, here in Bangkok, you can get them from Chinatown easily. Low cost, they are easier. I'm sorry, there is a typo there. They're easier in handling. Typically, they are multi-moded. I'm not sure of unless you do some pulling or so on, you can make it towards single mode. But yeah, they are usually multi-moded, largely multi-moded. Other example of polymer optics as well, or plastic optics, are lenses or optical element, and this been for going for some time, especially that we do imprinting technique to make micro lenses or milli lenses. Some of them are used by dropping, and so there is a very easy way to fabricate lenses, even optical elements. Like prisms and so on, and they are available in most of our optical mouse and all or CD player and so on. So they are available in many components. Lastly is the polymer thin film, which is not new, that we can spin coat any film, that we can make it in a viscous form, change of viscosity that will change the thickness and so on. So there are pros and cons in dealing with polymers in optics. We have done some work previously. So for example, here, if you see the work on the left that we did with Sulaiman some 4 years ago, where we use a plastic optical fiber, and we coated parts of it with zinc oxide nanorods. The reason we did that is earlier we proposed, and I guess in 2014 as well with Sulaiman, we did side coupling of excitation to the fiber. Mostly we use a glass fiber at that time, by putting zinc oxide nanorods. So you could just shine the light from the side, you get the light coming to the cladding mode, and even with etching you get it to the core mode. But here we did it with plastic, and I guess that was with Rafiz. So and we use that for extended source excitation, so do the structuring of the zinc oxide so you can excite from a larger source rather having a leak from a small source. Here is another example we have done with plastic fiber. For example, you could cut the edge of the plastic fiber into 45 degrees, and this is an easy process. And then that allows for wide field of view optical wireless receiver, and that's also done with a former student of Dr. Sulaiman. As well as here, if you align one plastic fiber to three plastic fiber with 3D printing technology, we developed a fiber sensor for biomedical application for back bending, and as well, this was one of the former Dr. Sulaiman students as well. So we have many work started in this way. So this is in fiber. We did other work where we use plastic or polymer. If what you see here, we did a printing with a PLA. If you are familiar, PLA is the most common 3D printer nowadays. You find it a very cheap 3D printer. And what we did, we printed one layer of cylindrical shape or cylindrical symmetry with variable variation into the radius here. And what we achieved, a sort of a beam shaping. The quality was not great, but it was a trial we did. And I believe with the newer printers, we could improve it more. But this is one of the things. Another thing we have done with polymer films was to coat some polymer thin film, spin coating polymer thin film was actually basically PMMA over gold. So we make it very thin. And what does it do? It shifts the SPR toward the visible spectrum. So in this case, we can work into a higher sensitivity region. And this work we have done recently, it's published this year with AIT. So those are some few examples about work we have done. There are so many work others have done. I just picked some few of the work I was involved in. So this is just to give a feedback that polymer optics or plastic optics is a valid point of work that can be used, even though the optical quality of most of those material might not be perfect or might not compare with glass or commercial glass, but we can use it for specific or certain application, as we'll talk. So what brings us here back again? I mean, what brings us to this one that I used to work in plastic fiber. Now, what I found recently that the 3D printing technology can provide us with some reasonable resolution. Actually, it can go to 32 micron theoretically. This is within the cost maybe with 3,000 ringgit, Malaysian ringgit, for example, of a 3D printer. If you pay more, you can get better quality, but the price is decent. Actually, the printer we have produces about 50 micron, which is okay to make some larger scale optics, such as waveguide, multimoded waveguide, and so on. The way it works is a formation of layer by layer. So you could divide your structure into layers, and those layers will get printed as we'll explain later. And the technique or the printer we're using is called digital light processing, or type of a stereolithography. It's one of the types of the optical lithography. So in brief, the way it works, you get the light source coming from here. You have an active mask, basically a liquid crystal display, and the resolution of this display defines the resolution here, because with the imaging system define the resolution that you can print. You have an imaging system here, and then you shine a UV light, and the light cures when this moving base is here. It creates a layer, then the base move up, you print a second layer, you print the third layer, and the base goes up. So you form your 3D structure based on layer by layer printing. So this is the DLB printing. So this is just to give a view why this topic can be useful if we want to print any optics in one stage. And that is the main target in our work as we initiated. We wanted to print waveguides in one 3D printing step rather than doing multi lithography steps. So what we propose, and this we published already in Applied Optics, is to use an elevated waveguide. So an elevated waveguide means if you have a base, you have a ridge over here holding the guiding region. And you can see the simulation here shows that this formation can provide a good guiding. So this is what we originally we started our work in polymer optics again. So this is an example what we have done in the previous work, that we generated a waveguide, and you can see it's elevated. It's about 600 micron by 600 micron, so it's vastly multimoded. And however, as we will see later, it was not perfect. So if you see the example here, this is the light guidance through the waveguide, and you can see this is the ridge region. This is the failure attempt. This is when this tower region collapsed. So this is a collapse region. So you can see there is a leak into the substrate. What we wanted a high confinement into the guiding region. So it was, I would evaluate, it was an okay attempt. However, it was not a good waveguide. So this we have to see. If you can take a look here, it's a lot of leakage here, And you can see there is some sort of a periodical. This one come from the layering printing, and the quality of the resin we used was not optimum. However, we found it useful. So even though it was a very bad waveguide, what we observe here, there is a surface roughness created automatically by the 3D printer from the way it is printing. So the question that comes, it's not a good waveguide, but can we use it as a good sensor? Because sometimes you have a bad waveguide, have a leak, but this leak by itself is very useful for sensing. If you can understand the physics of the interaction of the substance you want to do and this leak, then you can possibly tolerate this quality of the waveguide into something useful. And this was the main point or turning point in the waveguide, instead of giving up on the bad quality of as a waveguide. So it's not a waveguide, but it's a leaky waveguide. So what we thought about here, we thought about scattering as a first thinking, that you have a rough surface, which is what we see here under the microscope. You can see there is a roughness. This is about 50 micron gaps here. So this roughness, surface roughness, causes a forward scattering and backward scattering. We can ignore the backward scattering at the moment, just focus our attention to the forward scattering. So the question present, what happens when a vapor comes? How this affect this scattering? Because what we know, or what we thought before, that the vapor diffusion within the polymer might cause something, or would cause something. We didn't expect it to be that obvious or that severe on the effect, and that's what brings us to think few times before we understand the mechanism and how to use that mechanism. So the question is, what this swelling when the vapor or organic compound go through the matrix of the polymer, it go toward dissolving it, but before it dissolves it, it creates a swelling. So the polymer start to swell, the volume increase. So what happened there, and how this can be used to affect or to be used as a useful optical sensor. So let's look at the polymer. It looks like scramble, but this is, let's say, the unswollen polymer. This is a polymer matrix, as you can visualize it. When the vapor start to present here, so actually polymer matrix, we typically in optics represent it with a uniform refractive index or an effective refractive index. When a vapor start to present here, you can see this region on the top start to dissolve, start to go toward dissolving due to the force the molecule push the matrix, and you create a region, you can assume another uniform region to the first order approximation with a refractive index NS. So you created now 3 layers. Here we had only the surrounding, and not here you have a cladding, which is the effective index of this region. And you have another region here, which has the effective index of the swollen part. And you have inot. So this is the optics point of view. So from the light point of view, we can think of it as a first order model, that you have the cladding region and then a swelling region, then the one that's not swollen yet. And of course, as the process goes in time, we expect that the swelling region to be expanding because it's a dynamic process. So how to look at the simple physics for that? Simply, we can just approximate it as a Fickian diffusion. It's from Fick's model. So if you look at the concentration of the vapor, we know that's the derivative of time equivalent to the proportion to the second derivative in space. So basically, when you start having a diffusion process, the probability distribution of those molecules go in a way. So how to solve this? It was in Morisawa work, where it's a simple unitless variable introduction. So if you do introduction of a unitless variable here, x over 2 square root of the dt, it's unitless. Then this simplify this equation into straightforward equation, first order equal or one variable. Actually, instead of having two variables, we get it as in one variable. Then in this case, the solution, sorry, the screen is just stuck. Then the solution goes as Z equal dn by d mu, and that gives you basically an error function. So if you can see here, I have an error function. And now, what is the important part here? The important part here that the boundary condition we set, because in the boundary condition we set here that the concentration at any point of time at x equals 0 is n naught. So I'm pulling the upper limit or the upper concentration to be always the concentration of the surrounding. However, letting the extension of the concentration to reach 0 at any point down without existence of molecules. So the solution it gave me, not to go in detail there, it gave an error function distribution that's function of both time and space. So if I look at the evolution of the distribution of the molecules, it goes in this form. So we can see this is a distribution of the molecules as a function of time. Okay, so and as we can imagine that the constant as molecules go through the polymer, the refractive index of the polymer, because due to the swelling, is decreasing. And again, following the same paper from that we use, the same reference we used before, we can approximate the refractive index in this form. So what do we have here? We have a refractive index that can decrease, the refractive index that increase from the cladding, which is a lower index, to the unaffected polymer, however, leaving us with a region of a lower constant or lower refractive index. So what does this region do? And that was the most interesting part of the work, that this region works as a cladding. So what happened when the swelling process starts to go in the polymer, it forms a new cladding. And instead of having air as a cladding for the polymer, now we have a cladding region formed by the swelling part. And this was the main interesting part and the most useful part in this one. So if you look at the mechanism here, so as time evolves, we can approximate this swollen region as a uniform refractive index with a thickness that's evolved in time. And the refractive index we assume at this point that evolve in time. And you can see it has a profile by itself. However, if we look at the average of the refractive index in that region, we find it's almost constant. So the refractive index of the swelling region is almost constant. However, the thickness of the swelling region is increasing. So in this first order dynamics, if you want to look at the swelling process to a very first order approximation, we can assume that there is an average refractive index, almost uniform and constant over time. The main thing that happened here is the increase of the swelling region, the increase of the thickness, this thickness of this layer. This seems to be increasing as time progresses. So in this case, this D is increasing. However, this N is constant. So this is the main first order approximation or a conclusion that makes things quite easier to think what will happen when we add to the swelling, we add to it the surface scattering. So let's look at the surface scattering. If I have a rough surface like that, and I take a segment of my waveguide. Now I will take, now we forget about the swelling at one point. So we already have a first order idea how the swelling will behave. Now we look how the scattering would behave. So in this case, if I take a segment for a particular guided mode that over which light bounces, I take a segment with a complete bounce, that the mode bounce, I will assume I will have a leakage coming from the forward scattering. I will ignore the backward scattering. So in this case, if I have an input to the signal in, output to the signal out, I assume that the leakage take this form, which is in multiplied by the exponential, where alpha s is the scattering coefficient, delta is the width of that particular segment. Then the output of that segment will be the input minus the leakage, or we can write it in this form. So in this case, if I attach multiple segments, if I'm attaching multiple segments of the same bounce, so basically every bounce I create a segment and then I attach multiple segments, and I will assume an n segment where n equal L over delta. Delta is the width of the segment, L is the total width of the waveguide, and the output will be simply that particular coefficient to the power n. So that gives us a straightforward approximation that the output will be input was multiplied to the factor to the power n. Now, where delta, I can approximate it as the height of that waveguide multiplied by the beta of the mode divided by k naught n naught, where k naught n naught is the coefficient, the propagation constant for the polymer. So, and delta n is basically the difference between n naught and nc. Now, what this model gives us, it tells us that the more scattering, the more leakage, the less output, the less leakage, the less output, which seems quite straightforward, but it's actually quite useful. It looks simple, but when we put it together, we'll see what happens. So we verify this model. Now, if the scattering coefficient is 0, means n naught equal n cladding, then the term here will go to 1. Then we have a 0 output, meaning there is no light. So the more, the less the difference between the polymer and the cladding, we have lower scattering, and that will give us 0 scattering coefficient. However, that will give us 0 output. So the model seems to be okay, even simply okay. So we put those two models, the one from segmenting the propagation of the light, adding the leakage effect. So we have here, and the swelling effect. So what do we have? Let's look at one segment where we add the swelling effect. So the swelling of the polymer will take a form of a cladding layer. We assume that this will be a uniform cladding. We are smearing out the surface roughness, so we don't have surface roughness here. So when we have a cladding here, then we have a new waveguide, basically. So as the swelling process develops, we are forming a newer waveguide because the cladding keeps increasing. And what happens when you have an increasing cladding? You have an evanescent beam going through here. So instead of having full power, full light coming to the scattering region, we have an extension of the evanescent tail reaching to the rough surface. What does it tell us? It tells us, theoretically, this should reduce the leakage. So I should reduce the leakage, because instead of having full bounce here, as a previous case, I have a cladding and I have an extension of evanescent beam, then I have a smaller leakage. Then mathematically, I can simply put it in this form, that to the term that represents the scattering, I add the evanescent field extension, which is kappa. Kappa is basically the square root of beta square minus k naught NST. NST is the refractive index of the swelling region as goes with time. and D is the width of the swelling region as it goes with time. So as DS evolve, we can expect this term to vanish to 0, and then we have full power, so we don't have loss. So that's of course the first order approximation, that as the thickness of the swelling process, as long as you are exposing the polymer to the vapor, the swelling region is expanding, then the power should increase. The output power, or in this case we represent the intensity, should increase. You can approximate the kappa, or the longitudinal wave number, as n0 minus nt squared. So you just take it in an approximate form, but of course it's not accurate, but we can, just to simplify. I mean, so we test our model in terms of analysis. So what we do here, now, this is finally the model that we will use in order to see or to test the hypothesis of the effect of the swelling. So what we say, that NS is constant. So that means we take an average effective index of the swelling region, and it seems not to change much over time. So we average over distance. So we take the swelling and we average the refractive index. It doesn't seem to be changing over time. D is increasing by time, and we can consider the fundamental mode in this analysis. We are not considering really multi-modes. You can, of course, if you want to be accurate, you can expand all the modes. Here we just try to see the trend of the analysis, or at least if we can explain the experiment. So the main issue we had, how to explain what we see, how to understand what's going on the moment we put the VOC and on the signal coming outside. So if NS is constant, and we assume the concentration of the VOC on the cladding is constant, so NC is constant, then the scattering coefficient will be constant. So this term becomes constant. The only variable that here seems to change in this first order model is the thickness of the swelling region. So basically, we say that in the NS is constant, then the only effect of the swelling at this point is D of T. Of course, it affects NS. It depends how much concentration you have of the VOC on the cladding region. But if we take that constant, then the only variable is the thickness of the swelling region. So if you, in this plot, you can see we simulated 300 seconds, and we put those parameters here at the red wavelength, and we assume that we take 10 micron by 2200 micron segment of that waveguide, and we can see the time dynamics obtained from this model. So based on the model that we demonstrate here, which is a first order model, we explain a sensing mechanism, which is actually as simple as it sounds. We will show, I'm going to only show two results, or two experimental results. It actually gives a very good dynamic range. We will see it soon. However, our sensing mechanism works at that. You have a presence of vapor. The vapor diffuse into the polymer matrix. And what happened is that the polymer is swell. So you have a swelling in the polymer. And we said the swelling of the polymer by time correspond to the thickness, increase of the thickness of the swelling region, as here. So you have a smaller thickness. So when you don't have, this is at time 0. So you can see at time 0, when the vapor exists here, you don't have swelling. So you have a strong leakage. Strong leakage comes from scattering, strong scattering like there, because alpha S strongly depends, or a scattering coefficient depends strongly on the difference between the refractive index of the polymer and surrounding. And of course, you have a full power coming here. So the total amount of leakage is high. Now, what happens when swell? You create a cladding region, You have an extension, you have a smaller leakage. So that's what the swelling do. So this is the formation of a cladding layer with the swelling. So, so you have a lower signal, you have a lower power reaching the surface scattering, then you have an increase in an output. And this dynamic should keep going. Now, it doesn't keep going forever. Actually, this dynamic should saturate. And this saturation comes from the fact that at certain thickness, the evanescent beam can no longer reach the surface. Then in this case, light doesn't see the rough surface. So it becomes a regular waveguide, and you expect to have a maximum output power. So this signal will saturate. So the saturation in the optical signal does not mean saturation of the swelling process. The saturation of the optical signal will mean that the evanescent tail would not reach further. When we know the evanescent tail extend within a few hundred nanometer, so if the swelling reach more than a few hundred nanometer, we don't see an optical indication of the continuity of the swelling process, unless, of course, of the whole waveguide swell, but it wouldn't happen in a short time of experiment. This is the last slide here. I'm just gonna discuss what we have experimentally. Actually, the work have started in the opposite order that I presented. So what we have observed here, this is the case when you put isopropanol near to the waveguide. So what we did, we put the waveguide, light in, light out, and we drop 50 microliter of isopropanol in the vicinity, and we close the chamber. So we make it in a closed environment, so it starts saturating. So this one is the time that the vapor was applied, and we record over some time. So this is the case of 50 microliter. Now, we thought originally that it will show a sudden change, but we didn't expect that this dynamics. When we see these dynamics, so we start to go back and think about the swelling process. And now if you can see that when you add larger concentration, the saturation seems to go into a larger value. And this is a point when you start the ventilation. So the signal, and you can see is a quite a good dynamic range from 2.3 to 1. So it's a high dynamic range in terms of a power measurement. So one thing is our model, the way we put it here, when I define the D of the swelling region, we set a condition that D of the swelling region at which the concentration dropped to 1 over E. And this is a bit limiting because that doesn't set the effect of the concentration on the swelling thickness. So this one limitation of this model. And if we put the model for the case of 2 different concentrations, the model would provide similar result. However, it's obviously here is not. So this is one thing of the limiting of the first order approximation we have. However, the trend will be similar. So it will follow the same trend. Now, another experiment we have done is to test the repeatability of the sensor. So, and you can see we have applied for a certain time, we open for ventilation, then we apply again, then open ventilation and apply and open for ventilation. So it seems to be working quite well in terms of swelling and then unswelling or deswelling and swelling, deswelling, swelling, deswelling. So in terms of a sensor, it works. In terms of a waveguide, it's not good, but it shows a feasibility. And actually, it's a working example that it works as a VOC vapor sensor. And the concept is straightforward. So I guess I will leave it here for questions.
All right. Thank you very much, Dr. Walid. So first of all, I would like to, okay, again, Dr. Agus Muhammad Hatta, could you please unmute your mic and you can have a question.
Okay, thank you, Dr. Harry. Good afternoon, Dr. Walid.
Good afternoon.
Nice to meet you at this occasion.
Yeah, thanks.
So
Same here.
yeah, it is also a nice presentation and nice work on polymer optics. Or I mean, you have a good, you have some interesting work. So I have maybe 1 or 2 questions regarding the swelling mechanism.
Yep.
So I mean, this works can be, this model can be used for example, diffusion process, like ion exchange waveguide model. That's very interesting. And then I mean, in this, in your case, you have the substrate have a larger refractive index than the graded index region.
Yes.
So I wonder what happened if in some model we may find that the swelling refractive index is greater than the refractive index NO. So I mean, yes, what should we do when we face that case, and then the model will be no longer exist for this case?
No, yeah, the model, this model actually, you can still assume that the whole assumption in this model that we force the assumption that the refractive index is lower. Let me show you right there. Here, in this equation, this where we put that the refractive index, and you can see that if n equal n naught, you will end up having nc. That means at the top part here. So we assume that nc is low, and when n is 0, you're going to end up having with n naught. So this solution of n, that actually what causes this limitation that we limit ourselves, that the refractive index of ns is less than nc. You could actually, if in the case that the refractive index will increase, we can look at it differently. We can look at it that if we have a matrix of a material, that the vapor just depositing in the matrix doesn't causing that large swelling. If the swelling, if the swelling is not that significant, then we apply effective index calculation of a host, that's the swelling region, and adding the effect of the refractive indices in the middle, like use Maxwell Garnett, for example. Then you can generate values of NS larger than NO. So basically, you just need to remove this equation and start putting a different way to extract the refractive index from the concentration of the diffusion process. So this one, it just basically limiting us to the condition that the refractive index will decrease. So that's the main limitation in this model.
And the second question is what happened if the swelling process? So in sensor application, we need to cleanse out the sensor region, and then how we can make sure that the sensor will, the swelling process will clean up
actually
the instrument.
Yeah, if the refractive, no, let me answer first one, that the refractive index increases, what you would expect to see, you expect to see the reduction of the power. Because if the refractive index NS increases, then you have more leakage here, more leakage here. So you have more leakage in terms of less guidance, and you expect that the power drop. Now, in order to make sure that we get rid of the swelling, actually we have done few things. First, we left the polymer for a long time till it, and we measure the optical power, trying to return back to the original stage where we had, and this is a long process. At some stage, actually, we had to work for 7 hours. We have to let it run for 7 hours to get back into the original state. So what we did to avoid that is to use lower concentration, shorter time. So we didn't wait for saturation. We limit the time as in the experiment here. So to make it more practical, okay, here. So what we did, we can see we didn't wait for saturation. We limited the calculation time. So in this case, we put a certain time window of measurement, and then we turn it off, and you can see it goes back again almost to the original state in a short time. So in this case, it become more practical compared to here. If you can see, it was taking quite a long time till we try before that we heat. We do a heating process. The problem with the heating, it affects the polymer itself. So after a certain point, we couldn't use it. So we found that using a short window of operation works better.
Okay, thank you, Dr. Walid, and also thanks for your former works on multimode interference.
Okay, thanks.
Also very great good job and good work. Okay, thank you, Dr. Harry.
You are welcome.
Yeah, not a problem, Dr. Agus Muhammad Hatta. So he's actually our collaborators in different university or institute, but we are very close. We just collaborate of our laboratory. Okay. Anything else? I think Nurul Hidayah, you can unmute your speaker and you can. Yeah.
Sure. Thank you, Dr.
Not a problem. Just
okay. Hello, Dr. Walid.
Hi.
Thank you for the very nice explanations. I learned that from the power time graph characteristics, we can trace the refractive index of the swelling region, which also brings us to the information of the cladding thickness. Yes. And my question is, so far, is there any direct measurement to experimentally capture the thickness of the swelling regions?
We didn't do that, no, because the thing is, first, we didn't have the facility to do that in terms of, and the fact that if it is swallowed at this point, if you take it to measure, it's already deswollen, because you can see in the graph here, once we remove it from the chamber, it deswell in within 2,000 seconds. So what we do usually when we do our characterization, we try to understand the physics and try to match that with the experiment, and then or look to a certain verification in terms of published work. It was not as straightforward that we could actually just take it, because you need to keep it in a chamber, and if you put it in SEM or so on, you need to vacuum for certain time. Once you vacuum, that's it. The whole thing is out. So that's why we are limited to test. We were trying to apply some Fabry Bureau, but the scattering didn't allow us to do that as well. So we were very restricted only to the model that we have. At least from our limitation, I would blame it to our limitation.
Thank you, Dr. Walid. Thank you.
Anything else from Nurul Hidayat? That's it?
Thank you. It's enough.
Okay, that's it. So the next question is coming from Dr. Achilles Patak. Could you please unmute your speakers and you can...
Very good evening, Professor Walid. This is Dr. Achilles from Chulalongkorn University.
Oh, hi.
Yes, and recently I've just started working on VOC sensors, and your presentation was very impressive. Sir, I have a few questions.
I guess I will meet you soon, right?
Yes, sir. Recently I've just joined.
Yeah. No, I think I will meet you maybe next week or something, right?
Oh, sure.
You are with Sharaslak, right? Working with Dr. Sharaslak, yeah.
Yes, sir.
Yeah, she's my former student. Yeah.
Oh, great, sir.
Okay. Yeah.
Okay, sir, I have two questions. My first question is, does this sensing is based on the swelling phenomena only, not on the shrinkage phenomena? Like I have already worked on some hydrogels in which I have just performed some pH sensors in which for some pH values it swell and for some pH value it sink. And this results our sensing response.
That's a good question. Our hypothesis is a swelling, okay? And it seems it follows the trend. So let's put it this way. We are not saying what we have here is a theory. This is actually a hypothesis that seems to be okay. So we put ourselves in a very good limit to the work. So we assumed it's a swelling process. And we try to find the physics that can actually explain independently. So we just put the hypothesis, try to follow the physics, and the result seems to have a good trend. So that makes the probability that it's actually only swelling a bit higher. But it doesn't mean that there is no other mechanism. Definitely there are other mechanisms could affect, but it seems it's logical enough that it's swelling. That's I would say, or to be more accurate, because the fact that the signal is increasing, so we have a reduction in the refractive index, that can be attributed mainly to the volume increase. That's what I would say. So we can discuss later when we meet. So
your microphone is still mute, Dr. Achilles. Yeah, it's still muted. Okay.
Sorry.
Can you do?
So, sir, my second question is about the selectivity of the device. Like in your last figure, you have shown only for isopropanol, not for other VOCs. So what is the effect?
I didn't show selectivity because we're still publishing it. So so not to have a conflict. It does actually have different response, and that's due to the diffusibility of the molecules because of the diffusion coefficient here. So it's simple as if you have different material. I'm sorry, just a bit. Where is it? From the early stage, from the Fick diffusion, basically. If you look at the Fick diffusion, here. Okay, sorry, just the response. Come back. Okay, here. So it comes here. So that become the main selectivity factor is the diffusion process between the different molecules have different diffusion coefficient, and that's it. And we actually show it experimentally for isopropanol, for methanol and ethanol. They do have different response. So we're my student from AIT is just getting it published soon, so that's why I didn't include it. But we show it experimentally.
Okay, sir.
Yeah.
Thank you.
No problem.
All right, excellent. Anything else from other participants? Ika Puspita. Okay, could you please
the mute.
Switch your microphone on, then consider your questions.
Okay, thank you. Good afternoon, Dr. Walid.
Good afternoon.
Yeah, I'm from ITS, and also my research is about biosensor. And thank you for your interesting talk. I have some questions. The first question is, if I'm not mistaken, you use your polymer rich waveguide for the VOC sensing, right?
Yes.
What is the mechanism of polymer swelling on the rich waveguide? Is it symmetrical on the X and Y axis, or only on the X or Y axis? Since the rich waveguide is really vulnerable to birefringence phenomenon, and what, how it happens in the polymer swelling in your rich waveguide.
Okay, that's a very good question actually. The dimension is a bit too large for us. It's about 600 by 600 micron. So for us, it was safe enough to assume it to be a slab waveguide in both directions. So the polarization effect is ignored in this model. So we assume that swell in all directions the same way, neglecting the effect that comes from these regions. So, or this region. So as I said, it's a first order. So we didn't take in consideration the polarization. It's actually, we have done with an unpolarized broadband light source. So we neglect the effect of the polarization in the model. So we assume it's a first order. So you assume it from here or from here having the same effect. That was the crude assumption that we had.
Okay, and if I'm not mistaken, you put the sample from the top of it. If you put the sample from the top of it, is there any polymer swelling on the side?
No, we put the sample. We put the here next to it. Actually, we drop a droplet next to it in a chamber. So we let it evaporate, and then hopefully it have a uniform distribution. So we didn't drop the solution on the top here. That was an early work we have done, but in the recent work, we just dropped next to the sample.
Okay. And the second question is, how's the temperature effect of on your sensing mechanism?
Okay, very good. We leave it at room temperature as possible. So we turn off the AC. We keep it as 20 to 25 to 26 degree in ambient temperature as most as we could.
And the temperature of your sample, does it give the effect to your polymer?
It should. Because temperature increases the dynamic, the kinetic energy of the molecule. So we expect it reduces. It should reduce the swelling if we increase the temperature. We haven't tried that. We have tried only to deswell, to fasten the deswelling process. So we put it on a hot plate for a certain time that fastened the process of the deswelling. But we didn't measure the small variation of temperature effect. I would think it will work as a temperature sensor in this sense as well, just by itself. But the problem comes, which I'm not a material expert, but I would assume that the polymer parameter might change to a more of a permanent effect with temperature, if I'm not mistaken, to a certain limit. So that we avoid adding a temperature or heat, because in the first time we have done that, we couldn't bring back the sample to the original condition. So we didn't observe, we didn't intentionally observe the temperature effect. Let's put it this way.
Okay, thank you. Thank you, sir, for your answer.
Thanks.
All right. Anything else? It's yeah, just 2 minutes left. Rary, do you have any questions?
Yes.
Okay, just have a go.
I just heard about the polymer fiber optic because it generally fiber optic it create from the glass silica. Why the polymer fiber optic is used for the vibration sensor? Why not else?
If I understand the question, why polymer fiber optics used for vibration sensor? Is it the question?
Rary, is that the questions?
Yes.
Are you asking about the vibration sensor with the polymer fiber optics?
Yes.
Okay.
Because it's very unique.
Okay.
It's
Yeah.
very unique.
Yeah.
Okay. So I guess if we're gonna look, let's put it this way: there are many vibration sensors based on glass fiber using grating, volume Bragg grating, or using surface grating on surface glass. So there are many ways you can measure vibration. It depends how you form your sensing mechanism. If you're gonna form it with Fabry-Perot, so any fiber would work, not necessarily just a plastic optical fiber. So when we talk about a sensor, it depends what the mechanism of sensing of vibration. Is it interferometric, which most of it should be interferometric. So single mode fiber would be better. So it have to be a glass fiber compared to the plastic fiber. However, the only advantage plastic optical fiber has is easy to handle. It's easy to cut. As you can see in some work we have done before, we have cut it at 45 degree and it worked straightforward. This will be a bit hard. You would need a lot of polishing for the regular fiber, the glass fiber, but it was easier here. So we just cut it at 45 degree and we just send the signal from 90 degree and we could get the signal in. So you could coat it with other things. That could be maybe part of the question. Is easily coated with other sample and like nanorods, or you can coat with nanoparticles. The main point of plastic optical fiber is the cost. I would say this way. It's not better than glass, definitely. but it can work as a sensor. It's cheap, available. As I said, you go to Chinatown, you can get it for a decent price. I'm not sure how much is it in Malaysia, but in Indonesia and Thailand here for 25 baht, which is 2.5 ringgit per meter. So it's easy to find. That's the main advantage. But as a sensor, it depends what mechanism you are building your sensor around. Here we focus on swelling because it's a property, or as we said, we put a hypothesis it's a swelling, which seems to be okay. Till we could prove it wrong. We could be afterwards. We can be wrong. Does that answer the question, really?
Yeah, I think so. That's pretty much clear. Okay, the next question is from Professor Ratna. Could you please just have a go?
Thank you very much, Dr. Heri.
Your voice is too
it's a bit
low.
far.
Can
Speak louder a bit.
Be closer
Okay.
to the. Yep,
Yes.
it's
Okay.
fine.
Okay.
Yep, that's fine.
Thank you very much. Wonderful presentation,
Thanks.
Dr. Walid. I think I am interested about the SPR sensor.
Yeah.
I want to know if have you done the SPR sensor to experimental work, maybe like to application to food technology or maybe for the health technology like this?
We did. We have with alpha toxin. My student from AIT, she have done, actually we have two works have done with SPR for food and biology. Actually 3 for if we add more. So we have done for alpha toxin, the toxic in food, where we do a surface functionalization, and we develop what we call Bangkok University SPR system, which we publish it in Photonic sensor, I guess 3 years ago, which is 3D printed SPR. So and I guess we have 2 papers that on it. Now then we do if you look up Xenia, is Zinnia, and you search up my name, you will find she has 2 papers where we did alpha toxin in food, and that was in food technology for detecting the toxicity of the coffee beans. If I remember correctly, that was for the coffee grains. And we used actually the BioSPR. That's straight. It's a very simple SPR system, and it's very cheap. We developed here. I would be more than happy that if you, I mean, when the COVID-19 ends, that some of your students we can build and you can take it. We build a spectrometer as well, so we can build this. We use an off-shelf LED source, and we build our own spectrometer. And then that become a working system as it is, and we develop the software for that. So for SPR we have, for biology we have done for albumin detection, for early kidney failure warning, and we did for HbA1c for glucose. Actually we had several work we have done for glucose, detection of glucose, because it finally all comes to the how you functionalize the surface, what chemistry. Actually, this is outside my league, so I always have a collaboration in that. I'm very bad in chemistry, so I usually tend to have a collaboration. So we provide the SPR, the readout system, the spectrometer, the software. Then my student will be with another advisor that have better experience in chemistry, and then we combine the work together. So that's how we did that. But I'm more than happy to transfer the technology for BioSPR. We could provide it hopefully after the COVID pandemic ends. I'll be more than happy that we receive students, they build their system, take it with them. We have done that before, so.
Yeah, sure. It's very potential collaborations. Thank you, Prof. Ratna. Yeah.
Please allow me to contact you via email, Prof.
Sure, please, by all means, please.
Thank you.
No.
All right, so it's 4 o'clock now in Jakarta time, so in Bangkok as well. So Please give applause to Dr. Walid and Dr. Mukul as the first speakers, and then we're ready to move to the last speakers, Professor Sulaiman from University of Malaya. But before we move to the third one, I'm going to share information about the international conference from ITS, which is Dr. Agus Muhammad Hatta. Is not this is a former of the head of department, but it's I think it's still responsible for the international conferences. So I would share the link to the chat. So please have a look, and then just feel free to submit your abstract or whatever your results as your activity in your laboratory, your research. So you have a chance to share with others, and then be ready for collaboration. So that's what we are supposed to have after the conference. So I will hand over this moderator to Professor Ratna Apsari to accompany and direct all the communications for the third sessions from Professor Sulaiman Anwati Harun from University of Malaya. So please enjoy the third session. Thank you very much.
Thank you, Dr. Harry. Finally, we move to our third speaker and the last speaker today. I would like to say thank you very much for University Teknologi Mara Terengganu, Malaysia, for this collaboration in webinar. Thank you very much for your participation in here with your student, with your lecturer, and for all of this. Once more, thank you very much for your collaboration. Hopefully, we can continue the collaboration after the COVID-19 is gone from away. Okay, and so Prof. Sulaiman, I think, is very popular people in Universitas of Erlangga because now Prof. Sulaiman as a young professor in Universitas Erlangga too. I think all of people in here, especially in Universitas Erlangga, have know who is he. So we want to know, we have 702 publications. Wow, wonderful. And so high index is 31 high index. Wow. It's very, very, I think it's excellent competency of them, of his. And so please talk about your presentation for us, and please
Okay, thank you, Prof. Ratna, for your nice introduction. And first of all, I would like to thank Universitas Erlangga, first thing for appointment as an adjunct professor for the last 2 years. I think this third year. Third years I was adjunct professor for Erlangga University, and also for organizing this meeting together with UITM, University Teknologi Mara Terengganu, Dr. Zuzilawati. So today I would like to talk about ultra-fast photonic and high power fiber laser on the different topic, on laser topic today. And okay, let me do the slide. Okay, I am from electrical engineering. I think most of you from Indonesia and Malaysia know my affiliations, but for others here, so I am from electrical engineering department located in Kuala Lumpur. I think most of you familiar with the UM. So today I will be introduced to photonics and laser technology, and then talk about the fiber laser, more basic about fiber lasers, and on ultra short pulse generations, how we generate the ultra short pulse through the mode locking process, and to introduce on high power fiber laser. And we just started on high power fiber laser for the last 6 months. So we have some preliminary result to share with you, and to talk about applications of laser and also our products. Okay, what is photonic? Actually, photonic is science of light. Photons is light is photon is fundamental particles of light. So if you see the light, actually is consists of the particle of photons. Particle of light is photon that have energy that can be related to the wavelengths. So so photonics or the light is actually a colors or wavelength. So today they are widely used in various applications, especially in the communications, in a DWDM system, or the components or the equipment are based on the photonics, and they also have been used in sensors, in medical applications, and many more applications. And the first revolutions of photonic actually started in 1960 when the inventions of laser by the Theodore Maiman that invented or firstly demonstrate on ruby laser that operate in the 691 nanometer, I think, red light laser based on the ruby crystal. And laser, as we know, is consists of 3 elements. The most important is the gain medium that Dr. Muku have given us various type of optical fiber that we can use as a gain medium in fiber lasers. And on semiconductor, the second element source that normally people use semiconductor laser for fiber lasers, and also we can use also flash lamp and also injection current for semiconductor lasers. So the third element, they should have a cavity, these 2 mirrors as cavities. And in fiber laser, we can use fiber bright gratings as mirrors, and also we can implement the ring cavity actually to generate lasers. So today lasers are widely used in medical applications, in remote sensing, and also in manufacturing. And the second photonic revolution is on the optical communication. That's why now we have a very fast internet connections because of the DWN technologies, dense wavelength division multiplexing network that that was made possible because of the inventions of the optical amplifiers. So you can transmit multiple channels simultaneously through the optical fiber and amplify that simultaneously. And at the end, so we can split the channels. So we can one single line, single core of optical fiber actually can carry up to maybe more than 100 channels. And today there is new type of fiber like photonic crystal fiber. It's been developed actually to find a new way how to transmit light faster, how to create more channels, to transmit more channels. So based on the photonic crystal fibers. And because of the second revolutions of photonic on the optical communications, so we find that the optical component become cheaper. So because the telecommunication industry already saturated, and people also try to move to other areas. So people are working sensor, fiber optic sensor, and also fiber laser for other type of application. And the advantage because now the most of the optical component is become cheap, very cheap because of the optical communication developments. And the inventions of EDFA in I think 1995, 1996, the commercially available. We use erbium dot fiber as a gain medium to get amplification at 1.5 regions, and the normally EDFA is based on the silicon optical fiber. I think Dr. Muku have detailed explained on the fabrication various type of silicon fiber for both amplifiers and also laser applications. And fiber lasers. Why fiber laser is important? Because we reduce the free, not involve the free space propagations. So alignment free. So the conventional laser, the problem with the conventional laser is alignments. So the setup will be bulky and also the alignment. So fiber laser actually provide alignment free system, immune against the thermo-optical problem because we use very long optical fibers. So the heat deposition is more efficient because the gain medium is larger. So they can, because the core size is very small, so they can produce the excellent beam quality, and because of the advance in the fiber optic fabrications, as them explained by Dr. Muku, so we can have the high gain. So the optical fiber can provide a very high gain, so more efficient systems, and can be diode pump. And now the semiconductor technology is advanced very well, so the pump source is become cheaper now, so much cheaper. And the market of fiber laser, you can see, is increasing. For example, 2016 is 1.9 billion for the market of fiber lasers, and fiber laser has been used in wide application from industrial machining, defense, medical, free space communication. 6G is mostly on the free space communication, and also LIDAR, and they have a very big market and not many players. And emission wavelength of the fiber laser is depend on the gain medium, depend on the what type of material we use, we dope in our fibers. For example, erbium can be used to get at 1.5, it's conventional fiber laser, normally it's based on thuliums. And thulium also widely now is widely used for mid-infrared in 3 micron, 2.9 or 3.5, 3.2 in mid-infrared regions. So in Zeblan, if you dope erbium in the Zeblan glass holes, so you can get amplifications or crit laser in the mid-infrared regions. And for example, thulium can use to get in the longer wavelength in 2 microns, holmium 2.1 microns, and bismuth in the shorter wavelength regions, and high power ytterbium in the 1 microns region. So depend on the what type of active medium that you use. So you can define your working operating wavelengths of your lasers. And active medium, so we know that this is energy diagram for where widely used fiber laser. For example, ytterbium, you need to pump with 975 nanometer. So the beauty is because optical amplifier also is pumped by the 975 nanometer. So the pump, the cost of the pump is very low. That's why many works has been done on the ytterbium. And another reason is very efficient because it's involved of two level, go up to F5/2 levels and go down. So only one level transition. So you can get the efficiency is more than 90%. So very efficient. So the second type of fiber laser is based on erbium gain medium that you can pump with 980 and also is 1450 nanometers. To get amplification is 1.55. So the advantage of erbium fiber laser is the components, chip component, because the same component with the optical amplifier for telecommunications application. But the efficiency is little bit low. It's about 30-40% compared to the ytterbium that have more efficiency. And if in 2 micron is very important for biomedical applications, longer wavelengths, and also for sensor applications. And for 2 micron, we can either dope with the thulium and also holmium. And we can pump with 800 nanometers or 1200 and 1550. So because we can easily generate laser at 1.5 cheap fiber laser, we can use as pump source here. So we can get efficient lasering at the 2 microns. So the efficiency for the thulium fiber laser is very good. Is comparable with ytterbium. Can reach about 90% efficiency. So that's why people say it can be a replacement for the ytterbium laser in futures. And they have other type of application, especially in the medical, because it's operate in the eye safe regions. And if you want to have the slightly higher wavelength, 2.1 micron, you can use holmium. That the pump source is 2 microns. You can use thulium laser here to pump holmium ion to get amplification, to get laser at 2.1 microns. And generating the pulse, because the more application require pulse laser, because we want to have the high peak power, so we need to have a pulse, high energy output, so we need to have Q switch laser, for example. So there's two techniques for the pulse generation, Q switching and Mach locking. So Q switcher or Q switching can be generated by modulating the Q factor inside the resonator, mean to modulate the loss of the cavity. So when you modulate the loss inside the cavity, you can generate Q switch laser that normally operate at the repetition rate in the kilohertz region. But the pulse width in microsecond to the nanosecond regions. Microsecond to the nanosecond regions. But if you require shorter pulse width, you need to use Mach locking technique. Mach locking technique, we induce a fixed phase relationship between the longitudinal modes of the laser resonant cavity. So you need to lock the phase of the lasers. So another mechanism, and interference between the longitudinal modes actually can generate Mach lock pulse. So Mach lock pulse is we can generate in the megahertz. Normally the operating wavelength in the megahertz region, and the pulse width can be tuned or can be designed from the nanosecond to femtosecond regions. From the nanosecond to the femtosecond region. So if you have a cavity, so we have two mirrors. So light go forward and backward cavity. We generate many longitudinal modes involved. So if we can lock these modes, actually we can generate ultra short pulse. We can generate the ultra short pulse, and the higher number of phase that we can lock, so we can generate a shorter pulse. So depend on the number of phase that we can lock. The higher number, so the shorter cavity length is better to get the better mod lock performance. So how to generate mod lock? We can generate using the various technique. And the important point is the mod lock operating wavelength depend on the cavity length. Okay, depend on the cavity length, and the pass width here. Pass width depend on L cavity length depend also on the cavity length. So passive mod locking can be initiated by the NPR technique or saturable absorbers. So these two techniques. So or we can use the nonlinear optical loop mirror techniques, nonlinear effects to play nonlinear effects. For example, to use the figure of 8 configurations here. So another technique widely used is NPR, that we put the isolators here. We put PDI, polarization dependent isolator inside the cavity. So you can create the intensity modulations here that can modulate the phase. So we can create the modulation of the phase and inside the cavity and generate the very good solitone pulse. So what we did now is based on the saturable absorber. So we can put the saturable absorber device inside the cavity, put saturable absorber. So you can generate the mod lock pulse. So various type of material can be used for saturable absorber. For example, sesame, carbon nanotubes, graphene, TMD, black phosphorus, many things, nanomaterials, and fibers based SA like the thulium, holmium fibers, metal nanoparticles. Is people have done or tried various type of materials. So the operations of SA is based on the Pauli blocking principle. So if you have materials, so saturable absorber, so when the light pass through the material will absorb the light depending on the band gap of material. So we absorb the light, and under the strong illumination, so the material become saturated, or the ion will be stay at the excited level. So it's become saturated, and then they become transparent. They allow light to pass through. So here they absorb, they block light, and then they allow light to pass through. So within one round trip time, so you can generate is very short pulse. And we can put this material in many ways. You can make the films, put taper fiber and coating with the saturable absorber materials. So many techniques actually to employ or to use to make the SA devices depend on the base materials. And normally we make the films. We make the films here. If the material is powder, we can use the liquid phase effluation technique actually to make the saturable absorber films. Or if liquid, we can put on the dish sheet fiber or tapered fibers actually. But this technique is have the high loss. So film have the lower loss. But the problem film is we embedded the material inside the polymer. So the polymer have cannot sustain the high temperature. The maximum for PVA is 300 degrees Celsius. So it cannot operate maybe for the high powers, for really, really high powers. And these are techniques, this is how we make the films. So we have the materials, we make the material solutions, and we have polymer solution we mix together. and we made the films through drop and dry techniques. And we characterize the films. We characterize, we use FISM to see the structure, the morphologies, and the most important characterization for ultra-fast generation is to measure the saturable absorption. So we can use a balanced twin detector measurement technique actually to measure the saturable absorption. We plot this graph, power intensity. We launch high intensity light into the films, and then we plot the transmission again the intensity. So we see at certain intensity, high intensity, the transmission will be saturated. So from this curve, you can get the parameters, saturable absorption, and also saturable intensity parameters. Okay, this is the term that we use for pulse characteristics. I not discuss further. And this example of the cavity, we have, for example, this we use this sheet fiber, nickel sulfide material coating on the tapered fibers as saturable absorbers. So we put inside the cavity like this, and we get the solitons operate at the 1560 nanometers. The energy here is about 3 nanojoule. It's quite low because it's more lot lasers. So it's operate at 21.1 megahertz, depend on the cavity. So this material, the modulation depth is around 30%. So. And then we get I think picosecond pulse here. So this is another cavity. We obtain the dissipative soliton. Dissipative soliton. You see the rectangular spectrum. So we can generate pulse with the rectangular spectrums with different pumping power. So that we generate different spectral width. Okay, the higher pump power we generate higher spectral width. So we get to balance the nonlinear and dispersion characteristics of the cavity, we add 115 cm dispersion compensating fibers inside the cavity. So we managed to get femtosecond pulse at 152 femtoseconds. The output is femtosecond pulse. And this organic material, recently we work on the organic material as saturable absorbers. This material, P.PSS, P.PSS materials that we embedded into the PVA film, and we apply as mode locker. So this the cavity, laser cavity, that we need to add a small SMF sections here. So the material have 50% modulation depth. So by changing this cavity, we can design different type, we can obtain different type of femtosecond lasers, different repetition rate and different pulse width. So for example, we get 3.4 megahertz repetition rate and 710 femtosecond. If we use 52.5 meters cavity length. If you reduce the length, cavity length, we get the smaller pulse width. We get the smaller pulse width. The example with 52.5, this with 52.5, we get 710 femtoseconds. This the spectrum, soliton spectrums. Okay, time bandwidth product is 0.417. Indicate the pulse is slightly chirp. And when we increase, we reduce the same cavity, we just reduce the EDF length. So we change the net cavity dispersion. So it reduced the net cavity dispersion to the minus 0.773. So we get the repetition rate 4.8. The repetition rate change because the cavity length change. So we get different type of solitons here. The pulse width is smaller. Pulse width is I think 500 something here, and the time bandwidth product is 0.750. Is smaller, so is near to the close the transfer limit TBP. So very good soliton. So if we reduce further, you get a better pass. Better pass here. We reduce further 22.5 meter cavity length. You get 400 femtoseconds. 400 femtoseconds laser solitons. Okay. But you see here that we see the peak power when the pulse width reduce, the peak power will be very high. Peak power is more than 4 kilowatts here, but 4.2 or 4.3 kilowatt peak power. So very high peak power for these monochrome lasers. Okay, this is the comparison table that we get. And high power laser. So this different type of laser. So we need to have high power. So so normally is CW operation. So normally previously people use solid state laser to get high power, and also CO2 laser, because they have several disadvantages. For example, solid state laser, they have thermal limitations. They can cause the beam degradation when power will increase. And CO2, they have the low efficiency. Maintenance is very high and very bulky. So to improve the high power laser, so we can explore on the fiber lasers. And you see here, if you see this graph here, the power of fiber laser exceed both of CO2 laser and NDA laser lately. So we can generate more power compared to the CO2 and NDA laser using the fiber lasers technologies. And in fiber laser, high power, we need to use the double clad fibers, a different type of fiber. So they consist of two claddings, inner cladding and outer cladding. And the pumping is done through the inner claddings, and laser at the core. Okay, so the limiting factors for the high power, you see end facet damage. Of course, when you have connectors, high power, they can easily damage the end facet. So maybe in connector, or the connector must be made metal connectors. So the fiber should be metal, coated by the metal, so to reduce the damage of end facet. And thermal effect, they can burn easily. Fiber laser can be burned easily because of the high powers. And the nonlinear effects, when they operate more, so the quality of laser will be reduced due to the nonlinear effect. They can generate the stokes. And another limitation is the availability of pump power. But now we have the maximum MMC, ability of pump power, and also MMC. So, but now we can find the very high pump power, semiconductor laser, up to the 300 watts for one piece of the laser, very cheap. But another limitation is multi-mode combiners. So the technology of multi-mode combiner, if the commercial now, the maximum they can sustain is 50 watt, 50 watt per channel. So if you want to high power, you need to develop your own. So the commercial product, they have limitations. So a lot of limitations, the limiting factors is there, a lot of to study. And normally people use large mode area fiber actually to make the heat deposition more efficient. Because to avoid the limiting factors, so you need to make core is larger. Larger core means the heat can be distributed more equally, so can be removed easily. And this our experiment on high power laser. This a pump. So we have the pump here, 6 pump combined to the multi combiner. This pump, actually small pump laser, can generate 70 watts. So we have 6 pumps, so 70 times 6, so 400 watt. We can generate the 400 watt combined to the MMC to pump the ytterbium lasers. So we have done preliminary with this is they have standard ytterbium, this nuclear fiber, 15 micron core and cladding 130 microns. So we try a different length. So we get the laser at the 8 meters, we get very good laser with 44.5 efficiency. So currently we reach 40 watts. We are working to get more powers there because we have a lot of problem. The fiber is burned and the splicing point will be, we break, you know. We create the fire, we burn all your fibers, and the fiber very expensive. So ytterbium dot fiber is cost maybe 1,000 ringgit per meter. So sometimes you burn 1 meter. Handling is very important, and we need to go step by step because we have a lot of problems. So we find that if we use different, the dimension of fiber must be correct, you know. If 130 fiber, so we need, they cannot be we need to splice with the same size of the fiber. The size of fiber must be meshed. NA must be meshed. Everything is very important to make sure the fiber didn't break when the high power. Okay, this MOPA device. So we can, to get high power parts, we can use a MOPA system. So we have high power amplifier using the cladding pumping technology, and the femtosecond that we generate, it become the oscillator. We can amplify, so we get the high power. So this is for future works, and depend. Okay, the applications. So laser, ultra fast laser, mod lock laser can generate in the femtosecond and picoseconds, and Q switch at the nanosecond or microsecond. You see this application. So different type of laser have different application. For example, for continuous wave laser, so they generate more heat. So it's good for welding. Continuous wave, because they generate heat, is good for welding. If you want to do the cutting, of course, ultra shorter pass is better. Okay, in the medical, normally people use in the nanosecond to picoseconds for tissue ablation, LIDA. Okay. So you see here, if you use the picosecond, femtosecond laser, we can the cutting surface is better, improved. For medical application, people interest on the 2 micron fiber laser that operate in the 2 micron regions. So chirp pulse amplification, we can amplify the pulse using this chirp pulse amplification technology. The old technology, the Donna Strickland got the Nobel laureate because of inventions of chirp pulse amplification techniques. And the application, this one of our laser module. So you see inside they have laser diode controllers circuit, and we have laser diodes, and we have the laser cavity here, and then we have saturable absorbers. This and the application for 1 micron laser, for example, for tattoo removal, we can use, and for remote sensing. Pulse laser is widely used, and for LASIK, normally people use 2 micron, or mid-infrared. A lot of work for mid-infrared actually for medical application that operate the 3 micron Z-blunt erbium fiber laser. Okay, this example for tree planning to create the hole, small hole. Okay, this some example of applications of laser. This our product. So we developed pulse Mott-Lock 2 micron lasers, and also soldering system. So currently we are working to not soldering on the welding system. So we got the good funding from the government, working very hard now to generate at least 300 watt output power for welding applications. Okay, as a conclusion, the demonstration of first laser create the revolution of photonic and has changed the world. Photonic is actually a key enabling technology for various applications, for communication, industry, and medical applications. So fiber laser have advantages for producing a low cost, robust, high power light source for various applications. So we have developed various subtle absorber. We have published a lot on the ultra short pulse generation. We developed various type of subtle absorber. We demonstrate various type of Mott-Lock fiber laser using various game medium, ytterbium, thulium, erbium, and also recently on the neodymium fiber lasers. And we have also carried out preliminary work on the high power fiber lasers. And this Mott-Lock and power fiber laser, we have many applications for material processing and medical application that will be explored also for new applications. I think that's all for today. Thank you very much.
Thank you very much, Prof. Sulaiman. I think it's amazing presentation. So, are there any questions for audience?
Good afternoon.
Mary, okay. Mary, please.
Yes. I still interesting about this the fiber laser, but how to use the fiber laser? Sorry. What's different between the fiber laser and the another laser in the general? Example for the laser neodymium yttrium aluminum garnet. Is the laser neodymium yak or laser carbon dioxide or any other?
Okay, actually, the first advantage of fiber laser is smaller in size. In terms of size, is smaller. And laser, because the light propagates inside the optical fiber, inside the core, there is no need for alignment, alignment free. You don't need to align. For example, if you purchase femtosecond laser through the buck system, and the laser, for example, and you drop the laser, for example, the misalignment of the laser. So you need to send back laser to the overseas. Misalignment, very difficult to realign back the laser system. But fiber laser, we don't have this type of problem. So it's more robust, actually. It's more robust to apply. And it's smaller and it's cheaper, actually. It's cheaper. Because it's smaller, of course, the material is less. Material we use and it's cheaper. So the future will be on fiber lasers.
Hello. Assalamualaikum, Prof.
Salam.
I have a doubt in how Q switching fiber laser is different from Mott-Lock fiber laser. So what is the advantage in Q switch fiber laser compared to Mott-Lock fiber laser?
Okay, Q switch is operate in the kilohertz regions. So the pulse width is slightly larger, and the repetition rate
Yeah.
depend on the pump power. You can tune the repetition rate by tuning the pump power. Okay, so the advantage of Q-switch is on the energy.
Energy.
They can generate the higher energy. If you require high energy laser, you need to use a Q-switch.
Compared to mod-lock fiber.
Mod-lock have the lower energy.
Okay.
But the peak power is high.
Peak power is high.
Peak power is higher compared to the Q-switch, but Q-switch, the advantage is high energy.
High. So peak power is high in mod-lock, right?
Yes, yes.
And the higher energy is in Q-switching.
Yes, yes. High energy because the pulse is broader.
Okay.
So they have one pulse, we have more energy. Single pulse energy will be higher.
Okay.
So it's good for to generate heat. If you need heat.
Sorry.
If you generate, you want heat to use heat.
Yeah.
For example, for cutting. For example, if you want to, sometimes heat is not good, but some application you require heat.
For that, Q switching is.
You need to use a Q switch laser.
Okay.
So they have different type of applications.
Oh, okay, okay, yeah. So, and one more question, Prof. In the mode locking pulse characterization, that equation is common for Q switching also, or only for the mode locking? That repetition rate, pulse energy, and
yeah, the same.
Same.
Is the same. We characterize. We need to measure the pulse energy,
okay.
power, repetition rate, all these things. But the modulation depth, nonlinear behavior is important for the Q switch. Sorry, for the mod lock.
Sorry, Doctor.
It's not really critical for the Q switch, but very critical to the mod lock.
Okay.
The nonlinear characteristics.
Non-linear characteristics.
Like saturable absorption.
Okay, thank you.
Mahruf, yeah. So Rary, okay.
Yeah, I have a question.
Enough the explanation from Prof. Sulaiman.
Yeah.
Rary.
Yeah.
Mahruf, okay.
Yeah. Really, I got that.
For this is.
Thank you very much.
Enough.
Another question, maybe?
Yes. I have a question, Prof. Padi.
Oh, okay. Prof. Please.
Yeah, it's very interesting to your explanation concerning high power fiber laser. That means in this fiber laser we don't need to think about the polarization. It is polarization free in this system. Is correct?
In mod lock laser, you need to consider also polarizations, mod lock generation.
Yeah, when the Q switch laser, we don't care about it.
Not really critical.
It's not
really critical, but in the mod lock cavity, actually, you can optimize by optimization the polarization.
The polarization, yeah, okay.
You can optimize.
Yes.
But polarization very difficult to control.
Yeah.
That's why we cannot measure the polarization. Very difficult to control.
It's very difficult. Okay.
But when we fix, it's fixed. But if you move the cavity,
yeah,
you drop, for example, the polarization slightly change.
That's correct.
So if the polarization slightly change, maybe the output power will be slightly drop.
Okay. That's for the setting of polarization. It should be fixed, yeah, before we do experiment.
We need to fix. Sometimes depend on the cavity. Sometimes it doesn't affect so much. Sometimes it's effect. Yeah. Especially when you generate the femtosecond laser. So polarization very important.
Okay, the second question, how about for the mirror? Yeah, how to fabricate the mirror after we pumping, yeah, from the pump, light pump, and also go around to the the cavity. How about
so
the mirror?
We don't use mirror for the ring cavity. No need mirror because light oscillate.
Okay.
Resonate. But for the linear cavity, need mirror. For example, for high power laser, So it's based on linear cavity.
Okay.
So for example, if you clip the fiber connector also, you will get the Fresnel reflection 4%. That also can be used as a mirror, you know. For ring does not require mirror. You can put mirror also there. You can put FBG. They can control the operation. But for the mod lock, you cannot put narrow bandwidth mirror because they will disturb. Because when you get mod lock, the spectrum will become broad. When you get the femtosecond, the spectrum become broad. If you put mirror, the certain region they didn't reflect, so they can destroy the formation of soliton. So you cannot use mirror.
Okay. The last question concerning about the thermal effect. Yeah, if we need high power laser, fiber laser, normally it's broken. Yeah.
Yes.
How to overcome this?
That's
condition?
why you need to use large diameter fiber. Now people do large diameter fiber, mean the normal fiber is 1 to 5 micron.
Yes, yeah.
Standard fiber. So for fiber laser application for high power, they have a 2509 micron diameter or 400.
400.
But when you use a large diameter fiber, you cannot use the equipment for the communication. Because communication use 1 to 5. You need to use a special splicing machine. That very expensive.
Yeah, that's right.
So you need to use, but we got, now we will try 250 micron. So we purchased the splicing machine, so we can splice now 250. So can reduce the effect of burning because the power density inside the fiber is less because the core size is larger.
Okay, yeah. Because if I have experiment as I was in Paderborn, so I make experiment with my friend to make erbium dot fiber laser in lithium neophyte. So that's when the fiber optic always burn, yeah, because of the switch up and push. So it's broken always. Okay, thank you, Prof. Adi.
Okay, thank you, Prof. Ruby.
Prof. Sulaiman, can help me to close the share screen?
Okay. How to close? Stop share.
Okay. We can continue. Yeah. Okay. We can continue this. Okay. Another question for audience. We have the 7 minutes again. Please.
I just think about this. Yes.
Okay.
Do you want to ask again, Larry?
Yes.
Okay, please.
I heard about the laser from the rare earths, including neodymium and erbium.
Yes.
In the future, solid state basic, how to use for this? I mean the development of the solid state basic from the rare earths.
Okay, because different type solid state laser very important also. Because the pumping you cannot avoid using the solid state laser because the pump laser is actually solid state. You see my setup there. We have the pump laser, the 6 pump laser, all based on solid state laser, semiconductor laser. But semiconductor laser produce the lousy output. So low quality output. Actually, fiber laser technology is actually converting the cheap light, cheap photon, lousy output laser to the high quality laser based on fiber laser. Okay, they have different application. So both is complement each other. You cannot deny the advantage of semiconductor lasers. Okay, different laser, they have different advantage, different application.
Prof.
For example. Okay.
Prof. Sulaiman?
Yes, yes.
Can I have a quick questions?
Yes,
Just about related to Professor Agus Rubianto asked.
Okay.
About the energy or the power that we generated due to the whatever we choose. In mode lock or in the Q switch. For Q switch, the intensity or the power is actually very high. Not the intensity, the power is very high, but the mode lock is a bit higher intensity but less power. So in terms of the generating of the second or third harmonics, it's still possible to have the second or third harmonics for the for not the Q switch, for the mod lock, because in the higher intensity for the second or third harmonics, it's going to be very potential if we are using a high power rather than the intensity.
Of course, if you want to have second harmonic, mod lock is better because they have the higher peak power.
So the intensity is higher
power,
for the...
you inject to the nonlinear crystal, you can generate the harmonics.
Okay, so burning or damaging the sample, we're going to use the Q switch. Then for the second or third harmonics, we prefer to use the mod lock. Is that correct?
Yes, mod lock because the energy is less.
Yeah.
So they
But
generate
the
less
intensity
heat,
is high.
So they didn't damage the crystal.
Yeah, sure. Okay, thank you.
The question? There are 3 minutes again. Yeah.
Prof,
for the master student or doctoral student, please ask.
Yeah, I'm also a master student. So yeah, I'll ask.
Okay.
So 2-micron fiber laser means only thulium, right? Is it?
Thulium or holmium?
Thulium or holmium?
Holmium. This both.
Okay.
Okay. Pak Yasin online.
Okay.
Yes, he is. He is online.
Yeah.
So Prof Yasin need to ask the question, right?
Yeah.
The new dean.
Sorry, I have one question, Prof. Sulaiman. Yeah. I meet two medical doctors, specialists and dermatology. They PhD student focus and application of laser for dermatology like anti-aging. Yeah, they use first they use Q-switch laser, and then they move to picosecond laser.
Okay.
They inform me this is novelty for application laser for dermatologists. How about you comment? Which better, picosecond, and Q-switch laser for dermatology application?
Okay, because mostly the commercial laser.
Yes.
Normally they use Q-switch laser. They use CO2 laser. For the medical application, mostly they use carbon dioxide laser, gas laser, Q-switch. So depend for term for skin treatments. So it depend, but it's for the cutting. I think mod lock is better.
Yeah.
For tattoo removal, for example, you want to remove tattoo, you generate heat, you require heat. So you need to use Q-switch. Q-switch is better.
Yeah. Okay, thank you.
Okay.
I think it's enough because the time is limited. I think it's the final for discussion today. And thank you very much for your wonderful participation for the all of participants, and so for the University Technology Mara Malaysia. Thank you very much for the wonderful collaboration. And so thank you very much for all speakers, Prof. Suleman, Dr. Walid, and Dr. Mukul. And so for the all of the organizer, and so for all our student, yeah, bachelor student, magister student, and PhD student. And so thank you very much for this moment. For the last moment, please, Prof. Yasin, can the closing speech, 1 or 2 minutes, for the us, the new dean, please.
Thank you, Prof. Huda. Thank you very much for, especially for two last speaker, Dr. Mukul from India, Dr. Walid from Bangkok University, and Prof. Sulaiman from University Malaya. This today is we got the amazing presentation from three speakers. Yeah. Special request from us. I hope all of you accept my offer as academic panelist from Erlangga University and Physics Department. Thank you also for all participants for your patience during the our webinar. After this talk, I hope we can make collaboration between India, Bangkok University, Malaya, Erlangga, also ITS, UITM, Terengganu also. I special thank as partner organizer of this webinar. Thank you, Professor.
So the last but not the least, I think we need to emphasize to all of us that all the collaborations here is actually not boundaried by all of the university, but we can share, we can have all of our webinars through our collaborators. Means that, for example, ITS or Erlangga have the conference or the online webinar like this. So please free to join as the contributors, because this is the online webinar. So that's not belong to everybody, that's just belong to us. Okay, so feel free to join, to collaborate, and to participate as the speakers, or you can invite your collaborators as well to our webinar as well. So I would like to say that you're more than welcome to participate in the upcoming webinars, which is in 22nd of October. There's still about the instrumentations, but it's a bit shifted from the photonics. It's about the instrumentations and controls. All the collaborators are welcome, and feel free to join to the webinar. So that's all for the committee. If anyone needs to have some idea, you are more than welcome to put your comments on your feedback and chat rooms. Thank you.
For the photo session, please turn on your video.
Oh yeah, for the photo session, could you please just yeah, turn up the cameras, and then we will start from the first slide. Could the organizer committee as a, hang on, this is the first slide. I still have 2 participants not coming up yet, and the second one is still a lot. Could you please turn your cameras on? And then the third one is still a lot. Hello. Okay, everybody ready for cheers? 1, 2, and 3. And again, 1 and 2 and 3. Yep.
Okay.
The second one, are you ready? Hang on, I need to paste first. Or anyone else has done this one? Okay, just the committee can do. I just put okay. Oh, a lot of you are not available. Okay, ready? 3, 2, 1. Say cheers. Yeah. Good. And then the third slide. Yep. And 3, and 2, and 1. Cheers. And the last one. Could you please turn your camera on? Okay, whatever. 3, and 2, and 1. Excellent. Okay. I think that's all for the webinars today. So you're more than welcome to participate on the upcoming webinar on 22nd of February, 22nd of October, which is 10 days away from now. So if you have any webinar as well, you can share. So we will more than happy to participate as well. Thank you
very much.
and
Profesor
have a nice
Thank
day.
you. Have a nice day.
Thank you, Prof. Sulaiman.
Dr.
Thank
Mukul.
you, Professor Agus Rubianto. Professor Agus. I think for all of the participants, from ITS, we are more than welcome to participate in your
From
seminar,
Unity
and as well as we can organize the co-webinars
I think.
between ITS and UNER. And
Negeri Malang.
okay, UNM, okay, from Malang, welcome. Let's turn up from this webinar.
Thank you, Dr. Hari. Thank you, Professor.
Terima kasih.
Yeah, you are more than welcome.
Welcome. Prof. Yasin.
Sampai ketemu di
SPOA. Pak Eri.
Yeah, welcome to the SPOA.
Semuanya.
Gus, sehat Pak Gus. Prof. Ruby, Pak Asnawi kok diam aja ini Pak Asnawi ya.
Pak Asnawi.
Diam aja Pak Choirul Huda ini saya lihat.
Ya Pak Choirul Huda.
Nggak nongol, Rek.
Gila, Mas. Mantap dari jauh.
Sehat semuanya. Jangan lupa bahagia.
Nah, ini Pak Asnawi ini muncul ini.
Nah, Pak Asnawi muncul ini.
Salam untuk teman-teman di UNESA.
Dari National University of Malaysia. Ya.
University of Malaysia.
Atur nuhun, izin Bro. Assalamualaikum.
Waalaikumsalam, Mas Nurul Hidayat. Pak Yatno, ya tadi saya lihat Pak Yatno.
Iya Pak Yatno.
Dinyalakan dulu ini speakernya. Lama kita nggak ketemu.
Oh iya, lama banget nggak ketemu ini.
Gara-gara Mbak COVID ini ya.
Nah, ini gara-gara COVID ini sampai.
Iya Pak Yatno telat iki mau Mas
Ya kok dari tadi saya lihat kok.
Oh enggak, baru tahu kok. Katanya aku kok nggak dikasih tahu gitu loh. Duh,
iya.
ITS sudah tahu kok.
Pak, saya baru tahu dari Pak Asnawi tadi.
Monggo.
Yang webinar akan datang dari ITS bulan apa? Bulan ini atau bulan depan ada? Pak Yatno, mungkin ada update buat teman-teman.
Desember kalau nggak salah Pak.
Awal Desember. Ya ya. Nanti diinfo saja ke kami gitu, jadi bisa saling berpartisipasi gitu.
Ya, siap. Nanti insya Allah saya akan infokan itu.
Ya.
Pak Asnawi monggo juga. Ini
Negeri Yogyakarta.
Dari UNJ ya.
Oh ya.
Mas Hadi Nasbi, saya kok baru lihat.
Universitas Neng Jogja Bu.
Oh, Universitas Neng Jogja.
Mas Hadi nih Nasbi dari UNJ. Universitas Negeri Yogyakarta.
Monggo bisa dinyalakan apa mute-nya atau unmute-nya, Mas Hadi.
Ayo.
Mas Hadi. Ini ada Pak Febrian kok diam aja ya ini ya.
Oh, ada
Pak Febrian.
Mana Bu? Enggak ada.
Ada kok Rusdi nih.
Rusdi itu.
Sebentar.
Kami lagi lab meeting, Bu. Maaf.
Oh, iya.
Alasan itu, Bu. Alasan itu.
Ini ada Bu Yanti, ada Prof. Suryani. Mati tadi. Iya. Wis, sehat selalu ya, saling berkabar.
Alhamdulillah. Amin,
Bapak.
Prof.
Nggih. Salam kagum Prof. Arif nggih.
Nggih.
Prof. Arif nggih.
Terima kasih semua.
UNESA sekarang dekannya siapa, Pak?
Dekannya Prof. Mat Lazim.
Oh ya, salam nggih.
Oh, Mat Lazim. Oh ya.
Prof. Mat Lazim. Nggih, Prof.
Nggih, salam nggih.
Matur nuwun. Pak Heri.
Nggih, sami-sami Pak Yanto, bareng Pak Yanto.
Mohon izin
dulu,
nggih,
Pak
mohon
Heri.
izin nggih. Assalamualaikum
Assalamualaikum.
warahmatullahi wabarakatuh.